me invite Professor Narayan Nethalit to give his keynote talk. Yeah.
Good afternoon, everyone. Good to see everybody. So this talk is on manufacturing mostly. This is, again, cementitious materials, cement-based materials, cements, but mostly focused on the idea of how do you do low-carbon manufacturing. So a lot of our work over the last 5 to 10 years has been in that sector, funded by National Science Foundation, US Department of Energy, and now we have a manufacturing institute, one of the very large manufacturing institutes in the country, dealing with manufacturing of a variety of different materials that are carbon intensive: cement, steel, petrochemicals, food and beverage, all of that. So lots of this work is done as part of the center, and with my graduate students, collaborators in multiple universities, cement companies, infrastructure companies. So it's a wide variety of stakeholders that we have in this process. Right, so just to give you a very quick introduction, I won't go too much into it. All of you know this is very recent numbers, November 2025 update from the climate report. We are not making progress at all. 2030 is the target for 1.5 degrees Celsius rise, and you see that picture on your right, that the current scenario, the blue shaded areas, is where you're going to take it, and how much of a reduction and in carbon emissions that we have to do in the next 10 or 15 years to get to that 1.5 degrees Celsius mark. We're not going to make it. We're going to overshoot climate targets. But again, can we make now at least start making conscious efforts to change it and get to at some point of time? Global cement emissions is about 4.1 billion tons. This was last year. China still accounts for a lot of it. US cement production is pretty small. Compared to 4.5 billion tons of cement that's produced worldwide, US produces less than 100 million tons of cement, extremely small fraction. India produces about 500 million, China is about 1,500, 2,000 million. So the scale of cement production in the US is much slower, but it's tremendous amount of R&D, infrastructure and effort put into all of that. So kind of the emission scenario of where we are. And the other thing with cement, yes, we have lots of other materials, and you've heard in today morning's presentations also that concrete, because of its volumes that we use, and therefore cement by the volumes that we use, is what is causing this big impact. Whereas other materials may have a much larger carbon impact per unit mass or volume, but the volumes that we use are much lower. If you look at cement, it's also one of those sectors that has the most emissions per revenue dollar generated. So because cement is very cheap, you keep the denominator low, the fraction will go up automatically, right? The cement is very cheap, much cheaper than any commodity material that you can ever buy if you think of it. Right? In the US, we say that you won't even get a bag of potting soil for your lawn cheaper than cement. Cement is that cheap. So in that sense, your cost is per revenue, the emissions are much higher. Across the value chain, construction accounts for about 25% of global greenhouse gas emissions. Cement and concrete accounts for a significant value of that. And again, you've seen this. Where does it come from? It comes from the pyroprocessing stage. You have some inherent emissions because of limestone being calcined, calcium carbonate becoming calcium oxide and carbon dioxide. So that carbon dioxide is there, and you need 1,500 degrees Celsius. That temperature is generally provided by fossil fuels, which has a high carbon impact. So that second stage is what causes. Of course, there is grinding, little bit, transportation, quarrying, all of that. But eventually, our biggest control has to be on that stage 2, which is pyroprocessing. Now, there is inherent emissions. How do we control the emissions from limestone itself? There are ways of doing it. There's electrolysis-based methods that are being done to get calcium oxide out of calcium carbonate without CO2 emissions. There are non-carbonate sources, calcium silicate kind of cements, or cementitious sources that you can do. So variety of opportunities for us to do, but calcium carbonate being the most common one. Lots of cement companies, you have captive investment already done. You can't really change the investment to make a new cement. So you still stick with calcium carbonate. You live with quite a bit of the intrinsic emissions. Try to control that, clinker reduction being the most important one. So I'll talk about some of those as well. So here is the emissions from cement and concrete value chain. If you look at it, if you take all the way to your life cycle, all the way to the end of delivering concrete, cement accounts for about 90% of it. So again, how to deal with that is our major question. And in that, your chemical calcination process is about 50%, your fuels for heat is about 35%. So I'll give you a flavor of the work that we are doing in this area in both these aspects, reducing the intrinsic emission because of calcination, as well as newer ways to control the emissions because of fuels. So here is some very generic idea. You want to get about 75% of reduction in CO2 emissions by 2050 from cement manufacturing. Again, global numbers, because if you want to get to that 1.5 degrees Celsius temperature rise at some point of time, your cement involved carbon emissions will have to reduce by 75 or 80%, by hook or crook. It doesn't matter how you do it, it will have to drop down if we keep the kind of cement usage as we are using now. Again, we haven't really explored the expansion in construction that's going to happen as World Bank predicts in a lot of developing countries, in underdeveloped continents as of now. So that's going to be another big number that's going to be coming up. So if you want mitigation pathways, what are your mitigation pathways? Again, like I said, you have that 50% process emissions because of limestone calcination, and your thermal emissions about 40%. What are your pathways, right? Very obvious pathway to get to a lower process emission is to use less cement, obviously. Using lesser cement, using lesser clinker, other supplementary cementing materials, fly ash and slag and natural pozzolans and lots of different varieties of materials. We'll talk about some of that. You can use source of calcium other than carbonates, like I mentioned. Not a lot of other sources left. Even with calcium silicate, the processing demands are much higher. Carbon capture and utilization is a very strong strategy. For example, India emphasizes, China emphasizes carbon capture and utilization much more. In the US, CCUS is not that big of a deal, and you will know why, right? When you're manufacturing only 88 million tons of cement versus you're manufacturing 2,000 million tons of cement, carbon capture becomes very important for one and not very important for the other. But again, there are strategies that you can use for carbon capture. And like I said, CO2-less processes like electrolysis process to manufacture a cement. You're not really manufacturing cement, you're manufacturing the precursor. Again, you will see this lots of advertisement by saying CO2 less cement, we can do electrolysis and make cement. No, using electrolysis, you're making the precursor, you're making lime only. And lime to fuse with silica, you need to have some kind of way to do it. So again, it's not cement carbon free, reduction is already there. What are the pathways for reducing the thermal emissions? You can do alternate process heat. The biggest problem with alternate process heat is at 1500 degrees Celsius, your solar is not going to work, your wind is not going to work. It's very difficult to use many of these renewable technologies go all the way to 1500 degrees Celsius. You may have to tweak it. So what do? We may have to reduce the way in which you give the heat or your process temperature. Can we bring 1500 down to 1000, down to 900? At 900 is where limestone calcines. What do we do with the rest? Are there methodologies to do it? Alternate manufacturing process. Can we completely reinvent the manufacturing process of cement? Wonderful, I can do it in the lab. I can probably do a pilot process. You have hundreds of thousands of cement plants with so much of captive investment. You're not going to change them overnight. But is there a way to make some minor tweaks in the current manufacturing process? One of the big topics that we are looking at. And then renewables, energy efficiency. So I'll touch upon many of these and give you a bird's eye view of lots of these things that are happening. Right, so if you look at impact of mitigation measures, you will see these 4 different pathways commonly mentioned. if you do a lot of energy efficiency improvements in your cement manufacturing, which your cement companies have already done it, they are at their thermodynamic limits of energy efficiency now. The further improvement is only going to be very little. Alternative fuels. Can I burn whatever I get in my cement plant? If you ask a cement company, they'll say, well, are you kidding me? I'm doing that already. You give me Maggi noodles, I'm burning that too, right? So alternative fuels are there plenty. It's not really nothing much to do. Clinker substitutes. We are so fascinated in cement and concrete area by clinker substitutes. We love them because it gives all of us lots of opportunities to do research and publish. But clinker substitutes also in the longer term has its limit. So new technologies, new manufacturing technologies, and new even clinker substitute, new material technology. So that's where a lot of scope lies to get us to that lower emission scenario. So here is what, again, I'm looking at two quick ways of looking at currently deployable measures. So this is a US Department of Energy's recent report that they came up with to talk about where we will get abatement potential by 2050, about 30 to 40% abatement potential using currently deployable technologies like clinker substitution if you actually and very aggressively push them and take them to a much, much more efficient level. And then alternate production method, drop-in methods for traditional cements as well as any other cement replacement materials, you're looking at an extremely high market impact and a lot of abatement potential. And there are lots of other chemistries. Alternate binder chemistries, geopolymers, you hear about that a lot, but I'll skip all of that. Just talk about the first two. What does material efficiency mean? If we are, like in the US now, almost all of conventional OPC production has been done with. We don't have any more. Very few cement plants remaining that make pure OPC. It's mostly Portland limestone cement, where 10 to 15% of cement or clinker is replaced by limestone. You grind the limestone at the end of the process. That limestone is not calcined, so you directly get 15% reduction in your carbon emissions. So Portland limestone cements are there. And then the bigger brother of Portland limestone cements is limestone calcined clay cements, where because you're adding limestone, and once you have more of aluminates, limestone can react with aluminates to produce more carboaluminates. That strategy of limestone calcined clay cement, where India, lots of work has been done in that sphere. So those are the two major things that I talk about with material efficiency. We don't deal with slag much in the US because there's not enough slag in the US. That is available for cement concrete manufacturing. Blended cement with fly ash. We have a lot of fly ash, but all those fly ash right now are in the ground now. We are reclaiming fly ash now because power plants have reduced tremendously. There is no new fly ash, not too much of new fly ash produced. So lots of companies are reclaiming fly ash and using them to produce cement, but with very similar quality. And then blended cement with natural porcelains, picking up tremendously well. Lots of people, and if you go, lots of people are, I get samples and says, I have a new natural porcelain source, can you test it? Yeah, a little bit of silicates and aluminates will be there in any soil, right? And so somebody told them that silicates and aluminates and natural porcelains use it, and everybody is now saying that I have 1,000 acres of land, can I mine it for natural porcelains? So again, it's becoming another nice little business. So alternative binders, we'll talk a little bit about that. Green clinker, we'll talk a little bit about that. So those are the two things I'll talk about. There's lots of other things which are equally important, but we'll, for the sake of time, we'll skip that. Portland limestone cements, like I talked about, you have a small amount of clinker replaced by limestone. You create carboaluminate, a little bit of carboaluminate, mono and hemicarboaluminates. There is an optimal value in which you can use limestone to form actually reaction products, 3 to 5%. Beyond that, but since you are grinding limestone with clinker, limestone being softer, grinds itself to a smaller size, and when you have a smaller size, you have nucleation effects, filler effects, acceleration of cement hydration. You heard some of that in the morning session if you are paying attention, right? So all of those processes will get added up to your limestone process, and you can thermodynamically simulate how much exactly you want. Your porosity is reduced. You get almost as same performance as cement with about 10 to 15% lower clinker. Limestone and its synergy with aluminates, this is very interesting. Now when you have limestone, when you add more aluminates to it, you can have the synergy between limestone and aluminates creating much more reaction products, much more calcium aluminosilicate hydrates, much more carboaluminates to form denser reaction products. You have pozzolanic reactivity that is aided by the calcined clay, and then you have the additional reaction with limestone as well, creating a combined synergistic effect. You can replace cements up to 35 or 50% with limestone and clay. So here is one extension we have done on limestone and clay. So the way that you conventionally manufacture this is you take clay, you calcine the clay, and then you have limestone added, grind it, you get LC2, and that LC2 gets added to cement. That's your LC3, limestone calcined clay cement. What we have done is a minor change in the process. You calcine the clay, and typical clays, kaolinite has a calcination temperature of 600, 700, 800 degrees Celsius, depending on what it is. You calcine the clay to that temperature, but while you're calcining, add limestone also. Anyway, since you're calcining the clay, you're not adding extra energy, but throw in limestone also. Limestone is not going to calcine completely because you have to get to 900 to calcine limestone, but in this process, it will actually undergo structural and morphological changes to make it more reactive. So, limestone joins the ride with the clay being calcined, and you have now some additional effects. You get an SCM that's much, much more reactive. You can get to 70-75% of cement replacement using a co-calcined product. So you can see here some examples of what happens. The blue line on this TGA here is your kaolinite clay, and then when you have limestone calcined clay blends at different ratios, you will see that you have much more of mass loss or reactivity in that sense. Same thing with X-ray diffraction patterns. You can see all these Fs that I have circled here with the co-calcined limestone and clay are calcium oxide. So what happens is some calcium oxide is formed on the surface of limestone that's not completely calcined. You have a core shell, a shell of limestone, core of limestone and a shell of lime or calcium oxide that kicks up early reactions. What happens when you replace a large amount of cement with a cement replacing material? Your early age reaction, early age properties suffer. Now you give a little bit of lime to kickstart that reaction very quickly, very reactive lime. When you have on the surface, the reactions get much, much more faster. Now for a cement company, this gives a lot of different advantages. If you are a cement company with not enough of calcined clay resources, you can now make limestone, partially calcined limestone work along with some amount of calcined clay to do your work. If you have a lot of calcined clay, you can increase the calcined clay content by making the limestone more reactive. So now you can have enough levers for the cement company to play around with and improve the process. So we have a patent for this, which a couple of cement companies are very interested in. We'll see who buys it. And eventually goes. But the idea is easy enough for a cement company to implement without doing any capital changes at all, and that's what it makes it interesting for them. So it's only a minor change. Again, if you're interested in the reactivity, so the blue here on the left is the heat release or calorimetry curve for the plain cement, and then you can see all the LC3, your typical LC3 is that red one. You are now spiking the LC3 also. There's a question with water demand because of clays. Admixture companies are very good. They take care of that. I stay on the back and sit back and watch the show. It is possible. You can control all of that. So you will get, now you can see the strength. You can get much higher strengths at much higher replacement levels as well, both early as well as late rate strength. What about, so the question I'm always asked is, well, you're calcining limestone again, you're increasing the carbon demand, right? Yes, I'm increasing the carbon demand again, but the question is not always look at, when you're doing concrete, not always look at the total amount of CO2 emitted. What are you getting per compressive strength? Or, so what we are looking at is the strength per unit amount of emissions in this case. You want to higher that so that you can have reduced amount. Yeah, I'm almost done. So that's one way you can see that your limestone calcined clay systems are much more efficient. The other way is hybrid activation pathways for clays. We can, mechanochemical activation is very common. One of the things that we have, so what we do is change the structural order of clays by really, really grinding them with high energy and high intensity. Here is an NMR spectra for those of you who are interested to look at. You actually broaden your aluminide 4 and 5 peaks, which are the reactive aluminate species. You make the alumina much more reactive if you do this. That's what mechanochemical activation does. But then the idea now is add a little more of thermal kick to it, right? So you, instead of just doing mechanical, add a little more of thermal kick to it, because in mechanochemical, some of the reaction sites are not completely mobilized. A little bit of temperature mobilizes those reaction kicks. So again, hybrid systems to do it. So hybrid pathways, and don't worry about this math. It's all published. Anybody interested? It's all out there to look at it and how to design such systems from ground up. Efficiency, you can see that you will actually start to get much higher silicate and aluminate peaks in this system. So that's one thing. I have one more topic if Surya gives me 2 more minutes. 2 more, yes, right? So I want to reserve some time for interaction. Okay. So that was all the process part of it. No, the alternate manufacturing methods, and I've listed a lot of things that we're working on. Electrical calcination is something that we are going left, right, and center with. And there are companies that are interested in adopting some of these technologies. Plasma, we are getting you probably the world's first complete pilot plasma system for cement manufacturing done, where we have tailorable electric arcs for plasma and all of that. But I want to do this biofuel-based combustion synthesis idea. This is a 100-year-old technology that we are repurposing to see if we can do it for cements. People do it for ceramics all the time. We're seeing if we can do it for cements. So the basic idea is you mix the fuel and the raw material, and you heat it to the burning temperature of the fuel. And when the fuel burns violently, the internal temperature is much higher than what you supplied, right? So I supply 700, I get 1400 inside. So I need to supply only 700 to get my cement. In theory, very simple. So here are some really infrared thermography images to see how these specimens burn. The physics of the problem is actually a little more complicated. It depends on how it burns to get the right product. So you can burn it from outside, you can burn it from inside, the proportion of the fuel and the material controls. But we have calcined limestone using this method. We have gone up to making baelitic cements. Baelitic cements is C2S basically. You need only about 1200, 1300 degrees Celsius. So with about 700 degrees Celsius external temperature, I get about 1300 degrees Celsius internal temperature. And this process, ultra fast, cement is made in 2 minutes in the baelite synthesis. And if you really control the process, maybe about 10 minutes, as you see in this picture, to do that. So again, we have the other method of doing baelite synthesis. Just to show degree of hydration, very similar to conventional baelitic cements. You get the same performance. Scaling up, we are looking at ways to do, the manufacturing process has to be slightly different, but the entire paraphernalia for manufacturing is very good. You don't need preheater, you don't need pre-calciner, you don't need calcium capture system. None of this is required. It's basically a nice furnace, fancy furnace, like ceramics people do. So in summary, short-term levers are there where you can improve the performance of supplementary cementing materials. I've told you 2 examples, co-calcination of limestone and clay, and mechanochemical cum thermal activation, both of which will give you much higher performing SEMs, which means you can replace much more cement and be more carbon efficient, or you can invest more money and get new manufacturing. And all of these new manufacturing process, we are looking at modularization. So you can pick and choose, modularize, and replace parts of the cement manufacturing process as a modular fashion. And ultra-fast baelitic synthesis is one example of that. With that, I know I was very fast, but want to give you a bird's eye view of different things that are in this field, very new things that are coming up in this field. Thank you.
I think fantastic presentation, Professor Narayanan. I think we're running late by an hour, not our fault. Anyway, we'll have time for 2 or 3 questions. Please raise your hand if you have. Yeah, I see. Okay. I think the initial one I will take from a student there, and then I'll come to Professor Manoj. Yeah, go ahead. So you're giving the opportunity to the teacher, huh?
You guys have to decide who you want to ask.
Yeah, go ahead.
Mine is a simple question. Coal calcination probably is going to also evolve some CO2.
Yes.
So you're saying that the net effect can be reduced because you're using more of this.
Correct. Yeah, yeah.
Yeah, go ahead. You, that's, maybe, can you be a little louder? Do we have mic?
He's speaking louder.
Is there any settlement that we are looking for? Because making it more reactive, how much advantage we are going to get with that? Following with that, we know that the limestone available in different parts of the world, it's reducing by time. Means for cement production itself, we are having limited limestone. So what would be the best takeaway to utilize limestone, and what would be the future sustainability in that context?
Correct. So slight correction. We have no problems with quantity of limestone. We have lots of limestone. It's a quality of limestone that you have. You have low quality limestone in many parts available. And co-calcination is actually a good strategy to overcome that problem also, which I did not mention, because low quality limestone, you're making them more reactive when you start to add them as non-reactive ingredients in the cement. So that's one thing. With your LC3 reactivity, you will have LC3 is reasonably reactive, but if you have early age, if you start to replace much higher volumes of material, right, then your reactivity becomes an issue. So co-calcination overcomes that problem. Again, everything is tailorable. Like you do with normal cements, right? You adjust your ratios of different things. So there is no one size fits all. You can adjust your reactivity based on what it is. Your whatever isothermal calorimetry that you're getting in the lab is not going to be your final product. Your final product is going to be what are your ingredients that you're getting and how are you processing them, which are all tailorable.
Thank you, Professor.
Sir, you're good.
Okay.
So I did not understand the part where you said that when you mix fuel with the raw material, by the internal temperature increases much more than the energy we give it externally.
Correct.
If you could just clarify it.
Yeah.
one more
So what you're doing is you're adding a fuel that has a certain combustion temperature, right? And you're mixing and in a confined volume, and that's more important. You can't just do it in a random powder. So process has to be important. In a confined volume, you have a certain amount of fuel that reacts. That energy is going to be transmitted much violently too. Again, there is heat transfer processes that need to be controlled, particle-to-particle contacts, porosity, holding time, lots of different variables. But if you control it properly, the internal temperature rises much more than what you provided for the fuel to burn. So if you give 100 degrees Celsius, if your fuel burns at 100, it burns and produces a temperature within that confined volume that's much higher than 100 degrees Celsius. And this heat release is much more rapid, so your reactions, for example, think about a cement kiln. The reactions are so slow and rapid. Instead of that, you are violently causing reactions. Now, there are downsides with a violent reaction. Control of a violent reaction is much more difficult. But if you're able to do that, that 700 degrees Celsius differential is worth it to try.
Understood.
In the interest of time, I think Professor Narayanan will be available.
Yes.
We can interact with you.
Thank you so much.
Thank you. I think again one more big round of applause for Professor Narayanan.
Okay, now we are moving on to the contributed presentations. I think the first one is by Ms. Thakur. I think physiochemical and reactivity assessment of chloride-rich reclaimed coal ashes for their use as supplementary cementitious material. So you have 11 minutes. Maybe if we can finish it in 10 minutes, we can reserve 1 minute for interaction, please. Yeah.
So good afternoon, everyone. I am Mansi Thakur, PhD Research Scholar in Department of Civil Engineering, IIT Madras, working under Professor Manu Santanam and Professor Aslam Kuni Muhammad. The title of my today's talk is Physiochemical and Reactivity Assessment of Chloride-Rich Reclaimed Coal Ashes for their use as Supplementary Cementitious Material. So this is the outline from today's presentation, which includes the introduction, motivation, sample and material collection, followed by physiochemical characterization, reactivity assessment, and discussion and conclusions. So cement production accounts for 7 to 8% of the global CO2 emissions. However, we cannot completely stop using the cement, but the best alternative to reduce the usage of cement is use alternative SCMs, or supplementary cementitious materials. They will not just lower the carbon footprint, but also enhances the concrete performance in many ways. And these SCMs should meet the standard specifications as per the codes to be quantified as SCM. However, there are certain materials which do not meet these quality standards, and we call them as off-spec SCMs. The cause for their off-spec can be the variability in the combustion condition, fuel composition, or contaminants. Therefore, they need certain beneficiation process and a thorough assessment before their use in concrete or cement. Talking about the Indian scenario, currently 73 to 75% of the electricity is still generated from coal. And in thermal power stations, during combustion of coal, we get two byproducts, that is fly ash and bottom ash. Although we are using fly ash for many purposes, but not all of it get consumed. And bottom ash, because of its low pozzolanic reactivity and greater particle size, is not used much. So these unutilized ashes are mixed with water and are disposed of as slurry into the ash ponds. And annually, India generates around 300 million tons of ash. Talking about southern part of India, the thermal power plants which are located near the sea coast uses seawater for the ash disposal, which makes these ashes rich in chlorides. So there are a lot of challenges which are involved with the disposal practices, as they consume a lot of water and can harm the environment in many ways, like soil pollution, air pollution, etc. So by using these materials, we would like to turn a waste material into a usable source, which will help us to lower the carbon footprint from the clinker reduction also. So for my study, the samples were collected from North Chennai Thermal Power Station located in Ennore, which is near to the sea coast. The samples were collected from multiple locations and different depths within the ash ponds, and around 12 to 14 samples were collected, and one reference sample was collected, which was mix of all the depths and multiple locations. And these will be the abbreviations which I'll be using for my further slides. PAE is pond ash from Ennore. FAE is class F fly ash from Ennore. Now to check the variability of the chemical composition within the ash ponds, all the 12 samples were dried and grounded and were subjected to XRF. So from XRF, it was found that other properties were well in the limits of codal provisions for class F pozzolan material. However, the chloride content was high, as the maximum limit is 0.05%, and alkalis were also marginally high. For my further study, I used the reference material, which was mix of all. The ash was dried, grounded. It was grounded such that it meets the D50 size of class F fly ash. So black one is before grinding, and after grinding, we can see that the red one matches approximately equal to class F fly ash. Now the physiochemical characterization of the ashes were done. Initially, the pond ashes have high moisture content, which was addressed by oven drying. And fineness was also measured, and after grinding, we can see it become almost comparable to class F fly ash. Density LOI. The total chloride was measured using an auto titrator, which showed us around 0.84% is the presence of chloride in the ashes, and almost all of it is water-soluble chlorides, means NaCl, KCl, etc. Further, the oxide composition also showed that the pond ashes and fly ash both have similar chemical composition dominated by silica, alumina, and iron oxides. However, the difference only lies in the chloride content. Further, the XRD results also showed that the major phases present in both the ashes are mullite, quartz, and hematite. However, the halite, which is the NaCl, and potassium chlorides were found in case of chloride-rich reclaimed coal ashes. Looking on their morphology, mainly the class F fly ash has spherical shaped particles with some agglomeration and elongated spheres. However, the particle morphology of pond ash is a mixture of irregular shaped particles and spherical shaped particles. And after grinding, it was noticed that most of the particles became irregular in shape. The specific surface area also increased. Further, the reactivity of the ashes were compared. There were two tests performed, strength activity index and lime reactivity index. So for strength activity, the ASTM C311 code was followed, where a reference mix was prepared, And further, to assess the reactivity, the ashes were replaced by 20% of the OPC. And the water content was adjusted such that it meets the flow value of the reference mix. After demolding, they were cured in a saturated lime solution, and the compressive strength was checked at 7 and 28 days. The strength activity index is calculated as percentage ratio of compressive strength of ash replaced mortars to that of the reference. And as per the code, to quantify as SCM, the minimum limit is 75%. The second test was performed lime reactivity as per IS 1727, where the mixed proportion was taken as hydrated lime to SCM to standard sand, and the flow was adjusted such that it is 70%. After 48 hours, the cubes were demolded and cured at 50 degrees, where the relative humidity was maintained 90 to 100%. The compressive strength was checked, and as per the code, the requirement is to have the strength above 4.5 MPa. So this graph basically shows the results of both the lime reactivity and strength activity index. So from the results, we can see that the pond ashes qualify the minimum limit of 75% at both 7 and 28 days. However, the class F fly ash was not able to meet the requirement at 7 days, but after 28 days, it also crossed the minimum limit of 75%. And later, the lime reactivity results were also in line, where the lime reactivity strength was well above for pond ashes from Ennur, and fly ash was marginally lower than the 4.5 MPa. So overall, we can say that pond ash exhibits a higher overall reactivity compared to class F fly ash, and this can be attributed to the two effects. The first one is the chloride effect, where soluble chlorides enhances the dissolution of the aluminosilicate phases, which enhances the reactivity, which give us the early age strength development. And the second can be the mechanical grinding effect, where the particle size of these ashes reduced, and also there was a increase in the specific surface area. And also the grinding disrupts the glassy shell particles and exposes the reactive surfaces. So with this, I would like to conclude my presentation. So we have, from the study, we found that chloride-rich reclaimed ashes has class F pozzolanic characteristics and higher reactivity than class F fly ash. The enhanced pozzolanic activity can be attributed to effects of chloride acceleration and fineness. However, the high chloride content always limits their use as SCM because of the durability concerns. So if we refer to the literature, mostly people have used water washing, acid washing, or thermal treatments to remove the chlorides. However, this process again comes with high energy water usage and generation of secondary waste streams. Therefore, we need a sustainable and scalable alternative. So chloride binding can offer a practical approach in which we will try to immobilize the chlorides within the ash matrix itself. And the second can be using the chloride binding capacity of the cementitious matrix by using some chemical or mineral admixtures like TPA, TEA, or some calcium alumina source, which can enhance to form the Friedel salts, which are the mobilized state of chlorides. So these are the references. Thank you.
Very nice. Thanks for sticking to time. I really appreciate it. Yeah, we can have a couple of questions. Please raise your hand if you have any questions. Yeah, go ahead.
So you mentioned that you perform grinding of the
Yeah.
material. So when you say you have grinded the material, what is the criteria that you have taken care? Like how much is the time or is it a ball milling process?
Yeah, it was done in ball mill. It was done such that its D50 matches to that of class F fly ash. So here we have kept the class F fly ash as the comparison. So it was around 6,000 revolutions where I found it matched with the D50 size.
So you used to do it like check the D50, take a sample, check.
Yeah, like after a few revolutions, I'll take the sample, perform particle size analysis, and again continue.
So it's a trial and
Yeah, it's like you have to check again and again.
One more final question. In the interest of time. Anybody else? Okay, fine.
Okay, thank you.
There are no questions. Once again, let's thank Mr. Thakur. We'll move on to the next one is by Mr. Singh. He's going to talk on influence of hydration agent on reactive magnesium oxide based binders incorporating fly ash as a silica source. Yeah. You have again 11 minutes. Yeah. Try to wind up in 10 minutes so that we can have 1 minute for the questions.
Good evening, everyone. Since from the morning we have seen, like in inauguration, Professor Chi has started saying this thing, like Asia, the South Asia is consuming 85% of concrete. So 85% of the concrete is a bulk amount. Whereas when we talk about Dr. LP Singh, he said that we are having a target of 2027 for net zero. So I am Lalit Singh. I am going to talk about the influence of hydration agent on reactive MGO-based binder incorporating fly ash as a silica source. So I am a research scholar in IIT Jammu. I am working under Professor Raghu Mishra. So when we all are aware of this cement chemistry, like when we calcine the material, the temperature rises up to 1450 to 1500 degree temperature. So we don't have the control on the raw material. So sometime when the material is extracted from the source, the quarry, it contains some magnesite. So when magnesite is heated at that temperature, on the left hand side, when you see the process, the temperature 1450 and above, the magnesite become less reactive, and it causes less hydration and causes expansion in the binder. So this was the problem statement, but since I said I'm going to develop a material, making some tweaks in the composition and recipe, so I'm going to focus on 4 sustainable development goals so that we can cater the need of people who are in developing country stage. So my binder formulation contain MgO, fly ash, and the hydration agent. The hydration agent which I'm going to use in my material is magnesium acetate. So MgO, the MgO which I'm mentioning on the right hand side of my flow chart, it is a reactive one. It contains a calcination temperature of magnesite, 600 to 700 degree temperature. Then we will have a silica source from fly ash. We will have a hydration agent. So hydration agent will formulate magnesium hydroxide, and we will have two major product as a hydration product, that is MSH and MASH. So hydration agent, how it works? Generally, when you compare calcium oxide with the magnesium oxide, when we add water to the calcium oxide and when we add on the same hand, when we are going to add water to the magnesium oxide, the solubility is the main problem. So whenever we are going to add the hydration agent at this stage with the reactive MgO, the formulation of magnesium hydroxide over the MgO particle will cause a hindrance, and formation of MgO, magnesium hydroxide, will be limited. So hydration agent magnesium acetate start playing a game by acting as a dispersing agent, or in other way we can say it is a hydration agent. By that it will form magnesium hydroxide, that is brucite. Brucite will going to give the alkalinity to the binder system. So once the alkalinity is there, we need some silica source, because there is a limited number of binder having alkalinity, and without silica you can't make a binder. So in this case, fly ash, we are going to use fly ash for silica precursor. So at the end of the material, we will have a magnesium silicate hydrate. Since I'm going to study the variation of hydration agent, how the molarity of hydration agent, since I'm going to use this salt as a hydrating agent in a molar form, so I'm going to use different molarity for my material, and I'm going to study how the reactions, how the synergy will going to happen. So for the next few minutes, these are my mixed designation. I'm going to use OPC with, I'm having binary material like OPC and fly ash for a control mix, and other material having MF1, MF.75, MF.5, and MF0.25. It represents the molarity of magnesium acetate. So I have varied the binary material in the form of OPC 50% and fly ash 50%. On the same hand, when I'm going to use magnesium oxide and fly ash with different molarity, so I'm also going to follow the same binary composition for my material. So since I'm using it in concrete, the water by binder ratio I'm using it here is 0.4. So when I did compressive strength test for my evaluation of performance, then when we see OPC for the first case, since we are having higher replacement of fly ash, the strength goes down. And as we are going to reduce the fly ash content in OPC, because OPC will have calcium hydroxide, that will going to provide nucleation site for the fly ash aluminosilicate, and the product cash CSH will form in OPC case. But as I'm going to increase the fly ash content, the calcium hydroxide is limited, because OPC content is limited due to the composition of OPC. When it was observed, like when MgO 60-40 combination with 0.75 molarity, you will find the strength here. The strength is quite comparable. So in this case, the compressive strength seems to be okay with the OPC having 70-30 composition. But when we increase the molarity, the strength goes down in case of MF, magnesium and fly ash based binder system having 1 molar of magnesium acetate. On the right hand side, I only compare the magnesium and fly ash for the hydration kinetics, how MSH and other products are forming. I focuses on MSH. When we see the 0.75 molarity with 60-40 combination have the higher doses of MSH, though the MgO, the unreactive part of MgO is lesser in this case, but when we compare with the 70-30, the MgO here and here, they are way higher than the 60-40 combination of 0.75 molarity. This shows like we can go with the concrete having 60-40 magnesium and fly ash with 0.75 molarity of hydration agent, and formation of MSH will give a material having a comparable strength that compares with the 70-30 of the OPC and fly ash based binary binder system. So this is the formulation, the way I can contemplate the things like the formation of MSH has been represented here with the XPS, and I have come to know like MSH formation was there in MgO and silica band. Along with this, the confirmation comes with the MgO and oxygen also. So the XPS confirmed the formation of hydration product MSH, and along with the confirmation of MgO, unreactive part of MgO was found in XPS. For performance evaluation, I also conducted some tests containing water penetration and surface absorption. So for water penetration, since the compressive strength of 60-40 was found to be relative with the OPC with 70-30 and way higher than the 60-40 of OPC 60% and 40% of fly ash. So we have the data like we can conclude here with 60-40 magnesium and fly ash, we have a greater performance compared to the OPC with the same composition of OPC plus fly ash. I also conducted initial surface absorption test. It was in line with the performance which was observed in the water penetration test. So here the 60-40 with the 0.75 molarity have a good performance comparable with the 60-40 with the 60-40 of OPC and fly ash. So here we can see the trend of declining, increasing ISAT. The absorption value was found in 1 molar system of MF, the 1 molarity of hydration agent. So there were certain findings which I come to an end, that this source of silica may be derived from the stubble burnt ash. I have used fly ash. You can go for, since we are from North India, we can generate stubble burnt ash as a source of silica. Whereas the MgO hydration was improved using hydration agent, but the disclaimer comes with the molarity of the magnesium acetate as a hydrating agent. MgO and fly ash combinedly as a binary binder system have low carbon binder option. So we can come to this conclusion that MgO 60 and 40% of fly ash has a potential that it can have low carbon binder option. So thank you from my side.
Okay, once again, thank you, Mr. Lalji, again for sticking to time. Very well done. We can have
What is the cost of MGO?
Sir, right now the MGO which we are procuring, it is of 28 rupees per kg. Yes, the reactive one. Yeah.
What is the percentage purity?
92%, sir. Yes.
So that is the case, 60% of MGO would be.
Yes, for other source of MGO, we can go for the brine rejection material also, like from the seawater we can extract. We have immense MGO there. Yes, sir.
Okay. Dr. Piyush?
Yes, sir.
What's the reason for using magnesium oxide instead of magnesium hydroxide? Because MGO will convert to magnesium hydroxide, and that is expensive reaction, and that may happen very fast. It will not have time to react with the fly ash, which is slow reacting. So what was the rationale for going for magnesium oxide instead of magnesium hydroxide?
Sir, actually magnesium hydroxide is a deliquescence in nature. Means it absorbs water, the moisture. So we can't control that hydration kinetics. So once we start, since we have magnesium hydroxide in the form of chemical, we can have it. We can have silica source also, but we are not aware whether it has absorbed the moisture from the environment or not. Yeah.
Okay, I think no more questions. So with that, once again, let's thank the speaker. Thank you, Mr. Lalit. Now we'll move on to the next contributed paper by N. Kanga, who's, okay, you're there. I'm sorry, I don't know whether I pronounced your name correctly. He's going to talk about screening composite cement blends incorporating various calcine clay sources using electrical bulk conductivity measurement. So you can take about 10 minutes and then we'll have one minute for questions, right?
Good afternoon, everyone. My name is Tibe. I'm from the University of Leeds, and I just want to say thank you to the organizers for giving me the opportunity to share my work. So my topic is more of looking for like a rapid way of screening our cement blends, especially like blends with calcine clays, and also using a new method that is being adopted called the electrical bulk conductivity measurement. So the problem we have in the UK is we don't have a lot of SCMs, and so we are actually trying to find another form of SCM that we can use because as you can see, traditional SCMs like GGBS, they are in short supplies because the UK actually imports a lot of them from the EU and Japan, and so what my project is trying to solve is how can we find another form of SCM that we can use to mix with our cements to make low carbon concretes. So as I said, there's an urgent need for decarbonization, but one thing people talk about is decarbonization, but durability is also important because you don't want to make concrete structures that are low in carbon emission, but they are not too strong to, for the service life that they are prepared for. So as I said, calcine clays are solutions, but within the UK, we don't really have higher kaolinite clays that can help us to solve this problem. But also, apart from that problem, we also need to find out how we can make some form of adjustment to see how they can actually perform better as well. So what a lot of, my project is under a group called Eureka, and it's a combination of different universities, University of Bath, Imperial, and then BGS. So what we've done is trying to screen some of these clays that are available in the UK. We found out that we were able to locally source 73 clays, but we can see that most of the clays that are actually sourced are very low in kaolinitic content. And they also have some form of mixed clay mineralogy. So what we've done is we're able to classify the clays that we've got into different groups. So the group one, as you can see, were clays that had kaolinic content more than 40%, and then group 2 were a bit between 40 and 15%, and then carbonites as well. We know we can't use carbonites because you're supposed to have a particular amount of magnesium oxide and calcium oxide for them to be recognized as SCMs. And then we have group 4, which are a bit of a mix of different types of clay minerals, and then the ones that we couldn't take. So now you can see the picture that I have there shows that as much as we have these clays in abundance, but most of the clays that we've done the reactivity test on have actually fallen into moderate reactivity or unreactive clays. But what this picture does is it gives the industry partners that are working in an idea of where they can actually source the clays they want to start making LC3s. That's the purpose. So my focus is what is the role of these low purity, low cyanide content clays, and then how does that also affect the transport properties and chloride ingress, because we know that is one of the durability concerns that we have. So by adopting or recommending this model, we can be able to perform rapid screening of these cement formulations to be able to provide concretes that would be better. And so what we're proposing is in terms of assessing how the impact of the typical clay and replacements might affect it, and then compare all the calcine clays additions in terms of SEM1 and SEM2, because SEM2, as we know, is a greener type of cement. It actually replaces the energy-intensive clinker with limestone to reduce carbon emissions. As I said, the focus is to see how we can actually not just focus on reactivity, but also like other important aspects that contribute to the concrete becoming more stable and living the service life that is built for. So a picture on the left, on the right, sorry, is just one of the problems that Bristol is in the UK is actually trying to solve, where corrosion actually affected one of the bridges, and they had to propose a large amount for the fixing of it. So now, using this as a rapid screening tool, we know that, as I said, conventional SCMs, they usually only test, they focus more on reactivity and compressive strength, but they also miss a bit of most of the key durability drivers, which, as I said, are chloride ingress, permeability, and poor connectivity. And so this bulk conductivity test is a very good test that can be used to correlate how the pore network and the ion transport properties within our system actually works, and then we can actually use this as a quicker way to do a performance, a sensitive performance indicator. Also, the conductivity, so in terms of the bulk conductivity, offers a practical way of finding out how potential the durability of our concretes could be, and it also limits a lot of the conventional testing that are usually done based on literature. And based on this work, the recommendation will be to more like integrate this because there's a synergy in the sense of you being able to find out how the pore network, how open your sample is, and then try and avoid any form of transport, ion transport, because those are some of the things that contribute a lot to our structures being dilapidated. So my materials that I used were like 4 different types of clays with different keonetic contacts. You can see on the right is the reactivity test. So the R3 test, which we use, is used to kind of check how reactive these SCMs are. But we can also see that based on the R3 test that we did, we can see that the clays actually met the 90% medium criteria for reactivity. And we can also use this to produce enough extra products for hydration once it's activated. This is my mixed design. So how the test works is we put a paste sample inside a saturated vial, about 10 ml of water, And then what the thin film of this water does is it covers, the vial actually covers the specimens and tries to avoid any form of leaching that may occur based on the protocol. And then what we do is we wet some sponge that have 10 grams of potassium hydroxide that acts as a conductor for the paste, and then we take we measure the conductivity through the LCR that you can see on the right. So for SEM 1 and mixes with the clays, we can see that the bulk conductivity decreases with age due to poor refinement. But we can also see that SEM 1 is the highest because it has a high CH and it's more porous as well. But when you start adding the calcine clays rapidly, it densifies the structure and drops the bulk conductivity within this. And we can also see a trend of, in terms of the higher kernotin clays were the ones that perform better. Now looking at SEM 2, that's with 20%, we can also see that in terms of the 20% on the left, we can see that it's a bit weaker, but this could be because of the formation of secondary hydrates that actually give it a bit of a lower trend. But we can see when you compare to the 30%, there's still an improvement, but the same reactivity orders remains as seen in the first one where SEM 1 was added to the rest of them. So as I said, consistent early reduction in bulk conductivity, but there's still some increase in terms of the kaonictic content. And then also we looked at resistance of chloride migration. Oh, okay, thank you. Okay, yeah, so we looked at the chloride migration, and we can see that as well when we start adding calcine clays as well. We can see that the chloride migration coefficient actually drops after 28 days of curing. And we can also see that the ones with the 40%, which are the ones who are looking at the low purity clays, actually perform better. We also did some surface resistivity as well, and we can see that the 30% clays, 30% calcine clays with 50, kaolite content of 50 had like higher values of surface resistivity compared to SEM 1 and SEM 2, which shows that that actually helps in terms of refining the pore surface. And then we also compared the bulk conductivity with the chloride migration and the porosity, and we also saw that there's a strong correlation between the log-to-log in terms of chloride migration against the bulk conductivity, but it shows that the lower bulk conductivity reliably predicts your lower chloride migration, and that also gives you a better chloride resistance. And we can also see that the bulk conductivity is also driven by effective pore conductivity rather than total porosity. So these are just my major takeaways. Based on the work that we've done, we can see that as the higher kaonetic contents actually perform effectively, but even with the lower clays, they actually performed better than the SEM 1. We can also see that based on the comparison in terms of the chloride migration, the porosity and bulk conductivity, we can also use this as a useful screening tool. And also 30% replacement shows earlier reduction in conductivity than 20%. So we can also see that purity also dominates. And as I said earlier on, higher kaonetic clays with higher replacements give you a refined microstructure, lowers the chloride ingress, and gives you a better durable concrete structure. Thank you.
Thank you. Maybe we can have one question in the interest of time. Okay. I think looks like they have understood whatever. So good job. I think with that, I think we can move on to the next presentation. Thank you. Fantastic presentation. Okay, the next one is by
want to remove this?
Going to talk on performance and microstructural evaluation of magnesium oxide-based binders which are cured under sealed and carbonation. I think go ahead.
Thank you, Professor Suryam. Myself, Bhagat Singh, and I'm going to present the data of whatever my student has carried out in our laboratory. Well, I don't want to talk about why we should work on the alternative binders. From morning onwards, we are hearing from various speakers what is the necessity to work the alternative binders. And I'll jump to my background behind this topic. If you look at, especially in Asian as well as Indian countries, the paddy is the stable crop which we are using to as a major source of food for most of our countries. And if you look at the waste being generated from after the various stages in the paddy, the last one we are going to get about the rices cash. And if you look at the production as well as generation scenario in globe as well as in India from past few years, it is increasing year by year across the globe as well as in India. And we identified a couple of challenges to use RHA as efficiently to produce, especially in the various cements, which can use it for various construction activities. And the challenges I have identified and mentioned here. One is the proper characterization of RHA. This is the where most of them are still struggling to get hold of things, and also the measurement of the RHA reaction over a period of time. How does the RHA behaves when we add some additives to the cement as well as the binder? And yes, we also observe the performance consistency across the RHA sources. If you collect RHA source from one source to other source, how it's going to behave over a period of time, that's need to be standardized. This is one of the drawback we also observe. And on top of it, we have to develop a better analytical techniques which we can assess the RHA reaction pathways in a very shorter span. And we try to understand the characterization of the RHA. For that purpose, we have collected two different RHAs from two different source locations, named as RHA1 as well as RHA2. And this is the XRD spectra of RHA as well as the magnesium oxide. And we used the typical conventional magnesium oxide which is available in the industry. And we have collected magnesium oxide, one of the industry which has purity about 76%. And the RHA we have collected from two different locations, and it has various crystalline phases along with a broad amorphous hump over the 2 theta range. And the broad amorphous hump represents the glassy content which is present in the RHA, and we determined what is the total glass present in the RHA as well as the reactive silica. And the total glass is RHA1 and RHA2. RHA2 has the higher glassy content, and also it has the higher reactive silica compared to RHA1, as you can see it in the numbers. And we designed the experimental program where we would like to replace a certain portion of magnesium oxide with the RHA. It's a trial and error basis. Initially, we have started our work. And we used two different curing temperatures. And one set of samples we have cured under sealed condition. It's a atmospheric carbon dioxide. And another set of samples we have cured under the 10% carbon dioxide concentration. And our broad objective is we would like to understand how does these curing conditions is going to impact on the strength as well as the microstructure, and also how does these various product or phases going to form during the reaction mechanism, how these phases is going to impact on the strength of the product outcome of the product. Then we try to understand the reaction mechanism, how does the reaction is going to take place in when you replace RHA with the magnesium oxide. Well, this is the well-known, when we add water to the magnesium oxide, it will form the magnesium hydroxide. It's a quick reaction is going to take place. And in case of various, we have, when you replace with RHA as well as RHA1 and 2 with a different level of replacement, 50 as well as 40. And the peak intensity we have seen the two peak shape. One is at the initial few hours. After that, we have about after 18 hours, we have observed the second peak. The peak intensity depends on the RHA replacement level, the particle size, whereas RHA2 has the finer particles than RHA1, and the glassy content, and also the other parameters, how we are going to maintain the temperature and other aspects. Then we try to collect the samples from various segments. We try to investigate which type of product is formed in the different scales. And in case of magnesium oxide, we try to take the samples after 12 hours as well as after 24 hours. We found brucite is the only product is formed in the system. Whereas MgO RHA blends, we observed MSH is the major hydration product formed in the system with the few impurities we have observed around the magnesium oxide sphere. And well, the peak intensity depends on the how much glassy content as well as the fineness of our material. Then we try to investigate how does the carbonation is going to impact on the compressor strength in case of MgO as well as MgO RHA blends. Well, carbonation is clearly impact the compressor strength. There is no doubt about it after looking at these trends. But surprisingly, in case of RHA1, the more or less the seal and carbonation does not show much improvement to the overall system. Whereas RHA2, the level of replacement, if you do with the 50 to 40%, there is a clearly enhance in the compressor strength with respect to the carbonation. Then we try to investigate what are the products is formed in the system, how this product is going to impact on the compressor strength. And this is the typical XRD spectra of one of the RHA, and we have a broad amorphism that's classified as the glassy phase. And we do synthesize the MSH in the laboratory, that is magnesium to silica atomic ratio somewhere about 2. And this is the typical XRD spectra of the synthesized MSH. And if you look at the blends, this is the combination of these both the phases. We have the glassy phase as well as we have the MSH in the system. And you can see this is the blended versions. We have cured under sealed as well as carbonation. This is the right side one you can see. This is the typical XRD Ritweld quantified technique where we have separated glassy as well as the MSH with respect to the binders. Then we try to determine the various products formed in the system with respect to the age, both the sealed as well as carbonation. In case of MgO RHA mixes, the strength is majorly depends on the formation of MSH as well as in case of sealed condition, whereas in case of carbonation, the nesconite is formed after a few days. Maybe in case of RHA1, we observed after 28 days, we can see there is a formation of a nesconite in the system. Whenever we have the MSH, we observe there is a decline in the glassy content which is present in the RHA as well as the periclase is almost 0 in some of these cases. And if you look at this RHA2, the similar trend we have observed, surprisingly, the higher strength what we have attained for the carbonation, that is mainly because of the nesconite formation taking place in the system. We have about 25% of nesconite is formed in the system, as you can see in this figure. And overall, whenever we have the MSH formation and we have the nesconite formation, the periclase is almost the 0. There is no periclase in the system by 28 days. If you could have more periclase system, then we could have attained the more MSH or more nesconite formation that leads to the higher in the compression. This needs to be worked out how we can optimize the mix matrix. And we did some analysis by using FTIR as well as Raman spectroscopy where we can be able to identify the various carbonation bands. I'll try to complete. Yeah, in case of carbonation, we can see there is a clear bands. We have observed 1473 and 1411. This is because of the formation of the nesconite in the system. And same as with the Raman, we observe the D and G band. There is a shift in the wavelength over a period of time. That is mainly because of the formation of the carbonates which is formed in the system. Then yes, we try to understand the microstructure, whether these products are formed or something else is the form in the system. Majority of the cases we observe the nesconite as well as MSH. In few locations we observe the hydromagnetism which is less than 0.5% overall in the system. And this is the comparison of the overall trends what we observed as MSH formation is depends, the nesconite formation depends on the availability of the periclase as well as the glassy content. If you still we have the significant quantity of glassy content is available in the system, but we don't have periclase content in the here in the some of the mixes. Then this is the comparison of the how does the initial glassy content per gram of binder, how it's going to impact on the various products formed in the system. If we have the level of replacement, when we do the level of replacement, we should not blindly carry out the level of replacement. There should be a scientific novelty, how we can able to do the level of replacement based upon the reactive potential rather than trial and error based. That is what currently we are working on it now, and how we can optimize the various mix matter based upon the glassy content rather than doing a normal conventional way. Thank you.
All right, thank you, Bhagat, again for sticking to time. We can have a couple of questions. Welcome to Professor Surisha. I think, any questions? Yeah, go ahead. Yeah.
Hi, nice presentation. If I correctly see that Yours isothermal calorimetry results, the heat of evolution is for the mixers using the Rice's cache is less than 100 and it seems. But we generally, I don't know, we generally classify the reactivity of the material, whether it acts as a pozzolana based on the R3 test, which is only the reactivity of the material, which should be around 120, 150 and something above. But your overall heat of evolution is very less. I don't know how you are getting that strength. I don't, did you?
I'm just not trying to understand your question. Okay, then anyhow, I'll just let me think about what exactly you were trying to. We're talking about the R3 method? Or
Yeah, R3, because there we generally test the reactivity of SCMs or the pozzolans.
Okay.
So it's supposed to be around 150 to classify the material in different reactivity categories.
You were
So
talking
you are
about the pure RHA or you were talking
pure,
about the blends?
pure R3
But
test.
these are the
but,
blends.
Still, blends is very lesser than compared to that. I mean, it's supposed to be higher, right?
See, that nature of the material, from how we are going to depends on the particle size and the glassy content. There are specific surface area. There are n number of parameters is involved. That's the one
I
I think we
think,
should.
it's getting into a heated argument, so I have to
No,
intervene.
it's not.
So you can have a more discussion, during a coffee break, okay? All right, so any other questions? Okay, yeah, go ahead, Dr. Piyush.
Is that the dimensional stability of such system? Dimensional stability, like shrinkage or expansion?
Did you do any
No,
damage
sir. We have not done any of those things. Yeah. That's
It's
true.
scope for future work, yeah. Okay, all right, so thanks, Dr. Bhagat again. I think we are moving on to the last presentation, right? Last but not the least. So we have Ms. Rati. She's going to present on enhancing fly ash dolomite geopolymer concrete with graphene oxide, a path toward ultra high performance materials. So again, 10 minutes for you, 1 minute for question, please.
So good evening, everyone. My name is Manali, and I'm doing my PhD under Professor Anurag Mishra at IIT Jammu. So before moving into the technical aspects of my work, it is important to understand the environmental motivation behind the study. A major concern today is the slow degradation of the organic waste, especially the waste generated from the coconut-based products. Materials like coconut frond, shells, husk remains in the environment for the longer time without fully decompositions. So during this slow degradation, they release harmful greenhouse gases such as carbon dioxide, methanes, etc., which add significant to the environmental pollution. To address these challenges, the coconut waste, here you can see that they were thermochemically converted into the valuable carbon material instead of being left to decompose. So for example, the coconut shells, you can see here that they were heated at a high temperature of around 600 degrees Celsius under oxygen-free conditions, like undergoes pyrolysis and decarbonation. This process transforms the organic components like lignin, cellulose into the carbon-rich structures, while with the further treatment of this carbon can be converted into the graphitic material, eventually forming the graphene oxide, which becomes a highly functional additive for the construction materials. So eventually, what would have been like an environmental burden of the coconut waste can be transformed into the high valuable nanotechnology or a nanoparticle. So this not only supports the waste utilization but also contributes to the development of the sustainable high performance construction materials, which is a key motivation of my work. So the coconut shells is actually naturally rich in lignin and cellulose and hemicellulose, which are organic polymers containing carbon, hydrogen, and oxygen. When the shells undergo the carbonation, all the volatile components like water, carbon dioxide, and light hydrocarbons, which are released, what remains is a carbon-rich material where the carbon atoms start recognizing into the graphitic structure. So essentially, we transform a simple organic polymer from a coconut shell to the graphitic carbon, which becomes the base material for producing the graphene derivatives. So this is the synthesis process where we, the crushed coconut shells of 1 to 2 centimeters, they were washed with the waters so that the dirt is been removed. After that, we kept it in the oven for 100 degrees for 8 hours till it was dried. And then the KOH solution, which was prepared with the 2 molar impregnation ratio of 1:16, that is 1 gram of the coconut shell and 16 milliliters of the KOH solution. It is, and then it has been kept at the oven for 400 degrees until it gets dried. Then with the hydraulic presses and the tube furnace, we make graphene oxides. So this is an illustration that formation mechanism of the fly ash dolomite and a graphene oxide based geopolymer. So we begin with the fly ash, dolomite and the graphene oxide, and then we use the activator sodium hydroxide and sodium silicate, and by that we'll make a geopolymer concrete with fly ash dolomite and the graphene oxides. So here is the XPS analysis of the graphene oxide. So from here, XPS, we can confirm that the graphene oxide is oxygen-rich surface chemistry, and the oxygen and the carbon shows the active functional groups that engages with the SiOL and SiOSi networks. So this interaction enhances the aluminosilicate species and helps in the polymerization process. So this is the XPS analysis of geopolymer concrete with the graphene oxide composites. So from here we can see that the calcium Ca2P contribution has been increased, which indicates the formation of the hybrid NaSH and CSH gels. And the oxygen and carbon features the strong chemical interaction between the graphene oxide and the geopolymer gels as well. So here I have tested the compressive strength after 7 and 28 days. So for the geopolymer concrete with 10 molarity and 1% of the graphene oxide, we can see the strength increment of around from 46.37 megapascal to 65.84 megapascal after 28 days. Whereas for the geopolymer concrete with 8 molarity and 1% of the graphene oxide, the strength has been increased from 44 to 60.23 megapascal, which says that the graphene oxide improves the matrix densification and the gel formation, and hence the strength has been increased. The XRD and the FTI are also indicating, strengthening the strength results. So from here also we can see in FTI, we can see that the graphene oxide shows a stronger shift towards the 1,100 centimeter inverse. So that is for these SiOSi and SiOL bonds, which indicates the improved polymerization of the aluminosilicate networks. So we have done the Raman spectroscopy. So the Raman spectroscopy also indicates that from these pictures we can see that the graphene oxide is uniformly distributed within the geopolymer concrete matrix, and the interface modification supports the improved mechanical and the durability behavior. These are the SEM and TEM images. The SEM images indicates, as well as the TEM indicates, that the geopolymer matrix is well integrated with the that is graphene oxide, and it is a very highly compacted matrix with reduced pore connectivity. And thank you.
I think I request all of you to give a big round of applause. She finished well within the time. So good job. I think we can have a couple more questions.
This, how do you heat the coconut shell so that it is heated in absence of oxygen?
Yeah.
Or how?
In the absence of oxygen.
So can you just elaborate this thing, because I'm very much interested in this for a different use.
Yes, sir. So for this, we have crushed our coconut shells into 1 to 2 centimeters. Then we have activated it with the KOH solution. So the KOH solution, the ratio is of about 2 molar. And with 1 grams of coconut shells, we have taken 16 ml of the KOH solutions. And then we have stirred it with the mechanical stirrer. And then we have kept it in the oven for 100 degrees overnight. And then we have dried it. And then with the hydraulic press, we make some small pellets. And then these pellets is then again grinded. And for that, we got the graphene oxide.
Yeah, what is it becomes powder, absolutely?
Yes, sir, yes, after grinding it.
So what I want to do is this powder, I want to use it for the external, as a, mix it in the lime and then apply it.
Yes, sir.
This can last for many years, this application, particular application I want to use it. Thank you.
Okay. All right, so good. I think we can have more discussion with her on the process. Any more questions? So we can have one more. Yeah, Professor Surisha.
Yeah, very interesting presentation.
Thank you, sir.
In the final composition with geo and fly ash, did you use super plasticizers?
No, sir. For this, no super plasticizer.
Okay. So how did you have any difficulty dispersing?
Yes, sir. But in geopolymer concrete, when you are using sodium hydroxide and sodium silicate, so with the NaOH, the graphene oxide will, because it produces heats and everything. So for that reason, it will disperse in all these things. So, and here we can see that the dispersion is perfectly done with the Raman spectroscopy. So with the geopolymer, sir, because of the NaOH, it dispersed properly.
Yeah, so I'm just, yeah, that's a very good point. Do you think that there is any COOH bond at the geosurface?
Yes, sir.
And that might be one of the reasons.
Yes, sir. Yes, sir.
Yeah,
Yes, sir.
that's what
Yes, sir. Yes, sir.
Okay.
Well, yeah, I request you to interact with Professor Surisha and other experts. All of them are here, so take as much as inputs from them. Yeah, with that, I think we're coming to the end of the session. Hopefully, coffee, tea is outside. Still, it's hot. I don't know. We're delayed. Yeah, okay. Okay, so before that, I think I would like to thank all the speakers, including our Professor Narayan Naithlet. He set the stage on fire, but not exactly on fire, but on carbon emission reductions, different strategies, and so on. I mean, fantastic presentation, Professor Narayanan, and followed by all the five contributed papers, all of them presented very well. So I would like to thank all of them. Now I think the stage is yours.
Thank you all for your patience listening, and I hope you all have enjoyed the sessions beautifully. So now I welcome our Professor Anurag Mishra sir from IIT Jammu to honor the dais. Now I humbly request Professor Anurag Mishra sir to hand over a memento to our session chair. I also request Professor to hand over a memento to our keynote speaker. Thank you, one and all.
We have another exciting session after this. We'll take a quick 10-minute break. The tea is being served next to the Kohinoor Hall, not here, next to the Kohinoor Hall. And I request all of you to come back within next 15 minutes. Next 10 minutes. We will begin the session the moment you're back. Thank you so very much. I'm sorry. I think the tea is being served here itself for the sake of brevity of time. Please go ahead, enjoy your tea, and then we'll start in 10 minutes. Thank you.
Okay, send it to one of our email IDs. We'll load it. Okay, Anjan, email IDs.
Uh, Attention everyone. Please bring your presentations and load it in the laptop, whoever is presenting in the upcoming session, so that the process will be smooth, and since we are running out of time, I kindly request whoever is presenting, please load your presentations to the podium laptop. Thank you. May I have everyone's attention? We are about to start, so please kindly take your seats. We are about to start the second session. Kindly take your seats. Okay. Good evening and welcome back to the session 2. So today's session chair will be Professor Anurag Mishra. He is a professor in civil engineering and head Center for Strategic and Sustainable Infrastructure at IIT Jammu. His research interests include low carbon material and technologies for construction. He'll be taking over. Thank you. Over to you.
A very good evening and warm welcome to this session of ACECON 2025. Without taking any time, I would now invite Professor Vishal Ramesh Thombre for delivering the keynote today. He is Deputy Chief Engineer Roads Planning in Mumbai Municipal Corporation. And we have been working quite a lot in ICI. He is a PhD from Indian Institute of Technology, Bombay, and has been doing, because I don't want to read this whole thing, I can just tell you he is one of the person from the industry, and you would love his insights from industry to academia. In all the aspects, he is able to take any challenge to the established researcher in academia. So without, and white topping, he has actually pioneered in India in several states. In Mumbai, he has done it. In several states, it actually started percolating. I remember long back, we tried a patch in Jaipur also. Then we were in touch. It is long time, and I can tell you it is still working fine, right? So Dr. Vishal, most welcome. Please, all floor is yours. Just take 20 minutes, that's my request. Yes. Right.
Yeah, thank you, Professor. Thanks for your good words. Basically I'm from field, so I'll be discussing about field, what we had done on field. So not much theoretical, much practical. But before that, some slides I will show about Mumbai Coastal Road, which is now the talk of the town, and it will be followed with walkthrough. So it will be, many points will be clear. Why we need coastal road? Now directly I will go to point this slide because I had allotted 20 minutes, so I will stick to my time. Mumbai is a mega city, one of the mega city in our country. So lot of traffic is there. As we all know, in any mega city or any metro, traffic is the biggest issue. So this basically this project was to decongest the existing traffic. Background, yes, of course, way back in 2011, one committee was formed, some IIT professors, consultants, architects, all were involved. There was lots of studies, different alternatives were studies, and finally one was selected. We had appointed an international DPR consultant, and he has selected one alignment out of 8. Basically, this project is divided into two parts, phase 1 and phase 2. So I'll be talking about only phase 1, Mumbai Coastal Road South. The length of this particular is about 10.58 kilometers. It starts from Nariman Point and it joins to existing Bandravali Sea Link. These are the different packages, package 4, package 1 and package 2. Package 3 was combined. The best part of this project was that before inviting RFA, before inviting tender, we had acquired all the NOCs from government, because we all know basically it was an EPC contract. So when any contractor gets is awarded the work, he has to take number of NOCs, and it takes at least 1.5 years in taking all these NOCs. But before inviting tenders, we had we had received all these NOCs, so time was saved. Different studies was done before, during and after these projects. Study by Central Marine Fisheries Research Institute, Warsaw, study by NIO, National Institution of Oceanography. So these are the studies which we had done. And these are the NOCs which we got from different agencies. This is the salient features of this project. Length is 10.58 kilometers, road on reclamation is 4.35, bridges is 2.19 kilometers. We had constructed 2 tunnels which are below the sea. The length of this tunnel is 2.07 kilometers. There are 3 interchanges. Length is 15.66 kilometers. Promenade, continuous promenade is 7.50 kilometers. Sea wall is there for 7.46 kilometers. In short, under one project, everything is there. Tunnels, reclamation, RE wall, bridges, everything is there. Interchanges. So, packages of this there were 3 packages. Package 4, Princess Street flyover to Priyadarshini Park. Package 1, Priyadarshini Park to Baroda Palace. And package 2 is from Baroda Palace to existing Bandra ceiling. So we had awarded this 3 package to different contractors. 2 were Larsen and Toubro, and 1 is SCC Hindustan Construction Company, which JV with Hyundai. The original period was 48 months. It was commenced in 13th October 2018. It is completed this year only, 26 May 2025. This is basically structure, organization structure. Municipal Commissioner, Additional Municipal Commissioner, Deputy Municipal Commissioner, Chief Engineers, and organization chart. Every package is having 1 PMC, and above PMC, General Consultant is there, and above General Consultant, clients, that is Municipal Corporation. So these are the different 3 interchanges on various points. One at Amerson Garden, another is Haji Ali, and third one is at Worli. So these are some photographs of Marine Drive. This is the interchange at Amerson Garden, is just near to Bridge Candy Hospital. This is second interchange at Haji Ali, near Haji Ali Dargah and Mahalakshmi Temple. Third one is at Worli Sea Face. So these are the 3 interchanges. We are having 2 tunnels. This is the schematic cross-section of reclamation area. We had reclaimed about 111 hectares. Out of these 111 hectares, 70 hectares were, it is meant only for green, open space, and remaining for roads and bridges. So we have created open space for citizens of our country. This is the cross-section of cross passes, because if any vehicle gets breakdown, if any problem is there, then from one tunnel to another tunnel through this cross passage, people can move. So at every 250 meters, we are having these cross passages. Project benefits: Mumbai Coastal Road will relieve traffic on existing road network to a great extent. It will help to improve connectivity between South and North Mumbai. Coastal Road will reduce, very important, 70% of time and 34% of fuel. We are having back calculation for all these things. Existing average speed is around 15 to 20 or 22 kilometers per hour. But after this project, it is 80 kilometers per hour. Before the Coastal Road, the time taken from Nariman Point to Bandra, it took during peak hours 1 hour 30 minutes. After this Coastal Road, we can travel within 13 to 14 minutes. Carbon reduction is there. Carbon footprint is about 1826 tons. About 70 hectares of landscaping area with kids play area, butterfly garden, jogging track, cycle track, all different facilities are there. Again, for any mega projects, it automatically generates employments. So these are the various challenges. Reclamation of, then reclaim seawall, interchanges, tunnels. So I think every slide I can speak about 1 hour, but due to paucity of time, so I will just move further. Uniqueness of this project is that at present, this is the biggest tunnel in India, having internal diameter of 11 meter and external diameter of 12.19 meters. First time we had used Sakado system. If you travel in any tunnel, there are fans for ventilation. But this is the new system, Sakado system. From one point, fresh air is blown, and there are no fans in between. First time in India, bridges and interchanges are being constructed on monopile. We had introduced monopile first time in India. Nowadays, what general practice is that 3-4 piles are there, one pile cap is there, and then your pile is there. So from bottom up to the top, only a single pile has been constructed. So that's why it is called as mono. Mono means single. We had come across with some corals, and it was scientifically relocated by government department. These are the photographs, and these colonies are now increasing day by day. What I'm trying to say is that after constructing or during construction of this project, marine life was not disturbed, and it was taken care by different agencies. Now this is of package 4. Tunnel is about 2.7 kilometers. Cut and cover is 0.63 kilometers. Ramp is 0.65 kilometers. Surface area is 0.7 kilometers. We are having cantilever promenade about continuous 1 kilometers. For this particular project, we had reclaimed sea up to 10.5 hectares. Seawall is up to 0.6 kilometers running meters. Traffic management, there are different, as we know, there are different now method systems. Latest system we had used for traffic management. SCADA system has been used. This is package 1. These are the details of package 1. The reclamation is about 68.32 kilometers. Bridge is about 1.33 kilometers. These are all the salient features. This is package 2. Reclamation is about 31.59 kilometers. Interchange is about 2.6 kilometers. I will just show you the photographs during construction and after construction. This is cut and cover. This is the northbound tunnel. This is the ramp portion. Package 1. This is the interchange at Emerson Garden. This was very complex. There are 3 floors, one above the other, at Haji Ali near Mahalakshmi Temple. This interchange, again, Haji Ali. Navigational bridge. Now package 2 at Worli. This is the Worli interchange. These are the photographs. Currently, we are doing landscaping. Now landscaping will be completed within 6 to 7 months, where all butterfly garden, biodiversity park, jogging park, everything will be there. Again, this is the promenade. The width of the promenade varies from 20 to 22 meters. Such a huge promenade is there just near to the sea, beside sea. So people can leisurely walk continuously up to 7.5 kilometers. We are providing parking space at different locations, at Haji Ali, at Worli, and at Emerson Garden. There are 2-level car parking, and above garden is there. So it is below. These are the photographs. I will just show you the promenade walkthrough. Who is there? Excuse me. Cursor नहीं चल रहा है. हाँ. Yeah, here it's not.
Sir, it's in the extended screen, sir.
ये बंद. Basically, हाँ अभी ये ना मुझे वक्त दिखाना है. नहीं ये बाहर आ जाओ. Video, yeah. Many points will be clear through this walkthrough. Sorry, I'm little bit fast because time allotted is only 20 minutes. Voice nahi hai? I think there is voice, आवाज. Okay, again, these are the project uniqueness of these projects. This is the walkthrough. This is the Princess Street flyover. It starts from this is the tunnel. One lane is dedicated only for ambulance and firefighting. This last one in tunnels. Now, after coming back, after coming out of tunnel, this is the reclaim portion. ठीक है, no problem. Happens. Yeah. Everything is here. Okay, fine. It will take again 1 minute, I suppose. Huh. already completed traffic is flying on this particular project. As I said previously, before this project, people used to take 1.5 hours to reach from one point to another, from Nariman Point to Bandra. After this project, it takes hardly 12 to 13 minutes. There are no signal, there is no toll. So I would request, please come to Mumbai and visit this project. Thank you so much. I think I was in time. Thank you so much.
Thank you, Dr. Vishal. I think for this presentation, we must have given you more time so that you could have taken very quick questions if some. Yes, sir.
Yeah, very interesting project. I have two questions. One, my family lives near Haji Ali, and I didn't see any promenade in Haji Ali. And second, when I visit them from the airport, you didn't mention how long it will take, connection between South Bombay and the airport. Now it takes 1.5 hours.
Yeah, you can speak here.
Coastal road portion, it will take 13 minutes. And after that, it may take another 30 minutes. So previously, from Haji Ali to airport, it used to take 1 hour or 1.5 hours. But I think now, during peak hours, yes, it will take more time. Coastal road, 13 to 14 minutes. But after coastal road, again, some improvement is going on. So after coastal road, it will take another 40 minutes. And yes, sir, there is a promenade. So if you visit Mumbai after this conference, please visit. And you can walk on this promenade seamlessly up to 8 kilometers. Thank you. Thank you, sir.
Okay, anyone? One more question.
BMC is augmenting. Sir, to tell you, BMC is augmenting. Hello. Hello.
You can take.
Hello.
Seems I'm involved with this, BMC for reviewing some of their projects. So Municipal Corporation of Mumbai is augmenting, the traffic in Mahim Junction, which is quite a bottleneck. So now they are making 5+5 lane bridge. So which is now it is around 2+2 lane. So a lot of traffic from Haji Ali to Mumbai, even though on the LBS road will be, Swami Vivekananda road will be eased. And once the coastal road is over, then we get Warsaw Bandra Sea Link. So once you cross Warsaw Bandra Sea Link, and then you come to the, Western Express Highway. So there may be some traffic towards the airport. So, but travel time, rather than how much time is required, travel time is reduced from your Haji Ali to the airport by half an hour.
More travel time is going to reduce once Warsaw Bandra Sea Link. Now construction is going on. After that, again half travel time will be reduced. So the construction is in progress.
See, for the audience, I must want to compliment the BMC engineers. All the BMC engineers, they were on the field during the COVID. And we all were sitting inside house, but they were on the field.
Yes, thanks. Maximum work was done during COVID period.
Thank you very much, Dr. Vishal. Maybe you got free hand also as far as the hindrances are concerned. So always exploit it. So next speaker is, because we can discuss that later on, right? Effect of composition on physiomechanical properties of calcium silicate hydrate literature review. So Mr. Amit Kumar. I don't have your affiliation, so could you please just tell that first and take 10 minutes. Maybe then we can see 1 minute for discussion, right?
The mouse is not working, I think. No. Extended mode में duplicate में कर देते हैं. अभी No, no, I do not. Can I change to duplicate mode? That will be helpful for me.
Right. అది కాదు project duplicate correct this would right.
Okay. So good evening, everyone. I am Amit Kumar, and I'm a PhD scholar at IIT Delhi with Professor Vishnoi. So today I'll be presenting a part of my PhD work, that is effect of composition of physico-mechanical properties of calcium silicate hydrates. So these are the outline of my presentation. So as you know, concrete is a complex multi-scale composite. What we see at a macro scale looks like a homogeneous material, but as we go on a lower and lower scale of observation, we realize that it is actually heterogeneous. So the properties of these materials at micro scale actually affect the macro scale behavior. And this is my this is my PhD area, which predicts macro scale behavior through analysis of micro scale behavior through multi-scale mechanical modeling. So we understand that CHS is the primary binding hydrate, and it governs most of the mechanical properties at the macro scale level. So understanding CSH is crucial. And even CSH is a multi-scale composite, and we require different experimental techniques at different levels to have a complete picture. But nonetheless, a coherent and complete picture of CSH is still missing, and it is not yet clear. So most of the complexities arise at the mesoscale level, where we have only the options of models which explains the structure of CSH. And these are the 4 popular models from the literature. These can be divided into 2 categories, the colloidal-based model and the Feldman-Sereda model, which is a layered silicate model. So for modeling purpose, we understand 2 parts, that it can be modeled, it has a layered structure, and it comprises pores of several sizes. So for modeling purpose, we can model CSH as these type of bricks with pores in between them. And there are several factors that affect these CSH gels and CSH solids as well. So the presentation is focused on the solids part, where it can be represented as sheets and interlayer regions. These sheets can be characterized by the basal spacings and the length of these sheets. So the most important factor is the calcium to silica ratio, and they basically, on the structure part, it governs the basal spacing. Obviously, they vary locally, and we use the average value for this ratio. Similarly, the length of these silicate chains, they also vary, and what we refer to is mean silica chain length. And again, this ratio also affects the arrangement of the sheets. Similarly, another factor is water content, which vary with RH, and it affects the basal spacing and the arrangement of the sheets. Then there can be other factors like SCMs, admixtures, and other ions through, for example, alkali activated materials, and they again affect the basal spacing and the length of the sheets. On the behavior part, the temperature and stress affect the behavior of CSH. So as I discussed, this ratio of calcium to silica is perhaps the most important factor, although it varies locally and we use the mean values. So the effect of this calcium to silica ratio is that the mean chain length reduces with CSI, this ratio, that is understood, there the literature is coherent, coincides. But on the basal spacing part, the trend is not very clear, and we see quite a variation. But nonetheless, we can, the majority of these literature suggests a decrease of this basal spacing with calcium to silica ratio. Again, the arrangement of sheets is also affected by this ratio, and we realized the randomness of these sheets increases with calcium to silica ratio. However, we observe that the H by S ratio increases with this ratio, and at the same time, the elastic modulus in the three directions they decrease. So this is actually a counterintuitive observation, because if we are reducing the basal spacing, we expect that the elastic modulus should increase, and at the same time there should be a decrease of the water content in CSH. But actually the opposite happens. So there are several hypotheses in the literature to explain this paradox. One of them is that more hydroxyl ions are needed to balance the extra calcium in the sheets, and we realize it from molecular dynamics, and we see that more of the water is present in the interlayer region. And this hypothesis is supported by the observation that genite, which has a high calcium to silica ratio, has more calcium to hydroxide bonds and calcium oxide bonds, whereas tobermorite has only calcium oxide bonds. Then the another hypothesis is the loss of ordered basal spacing. This is a TEM image of CSH which was produced from C3S hydration, and we see at lower calcium to silica ratio, these sheets are very much ordered, but at this calcium to silica ratio increases, they lose the pattern, and there's a sort of amorphous arrangement or random arrangement we can see. Similarly, we see that with increase of calcium to silica ratio, the elastic moduli in the three directions they converge. That is, they behave more like isotropic with increase in calcium to silica ratio. So to explain this paradox, I feel that this can be a mechanism that these sheets they get closer with calcium to silica ratio, and there is more creation of this space here where water is filled, and that is why the water to silica ratio increases with calcium to silica. This can also be supported by this more curve in this TM image, that these sheets get more curved although they get closer. So more curved sheets means dense foil type structure. And a simple model can be proposed like the layered sort of model, where the sheets and interlayer can be modeled like this, and the loadings can be proposed from two directions, parallel and perpendicular to these sheets. And we realize that through these kind of models, we can predict the experimental behaviors. And obviously, this is not the actual morphology, actual changes in the structure, but for modeling purpose, we can do it like this. Similarly, we see in the creep behavior also increases. The creep increases with calcium to silica ratio because this creep modulus decreases with that. And the overall behavior, this is only for the solids, but the overall behavior of CSH is complex. It is not monotonic. It can increase or decrease with calcium to silica ratio because of the random arrangement of the sheets. So this was a short literature review. The possible future directions are that these mechanisms can be supported with more experimental measurements. And in real system of CSH, it comprises of more atoms, more ions like sodium, potassium, zinc, and a combined effect should be understood for a better understanding. Then CSH is a metastable gel that evolves over a decade. So the aging process can also be explored, and the slow diffusion of ions from other hydrates into CSH can also be explored for the alterations in the composition and mechanism of CSH, the mechanics of CSH over the long term. So thank you for your attention. Question? I finished in 8 minutes.
Thank you very much, Mr. Amit. And we have time for a couple of questions. A quick yes, yes, sir.
Yes, sir.
Thank you for the presentation. I just want to know about the calcium silicohydrate what we have in. If we add a mother liquor on the system, if we add a calcium silicohydrate precipitate in the system of cement paste, have you done any studies on that by increase of calcium silicohydrate?
You mean the quantity of calcium silicohydrate, CSH?
Yeah, CSH gel, if suppose we make an synthetic CSH gel.
Synthetic CSH,
yeah,
okay.
We put actually, any effect on the system of this calcium silica reaction?
You mean to say the overall volume of the CSH increase in the system?
Overall volume or what, chemical reaction further, goes on.
Actually,
By
I'm not.
increasing the CSH quantity,
Okay.
any increase in gel is there?
Increase of gel in the.
Yeah, cement paste. Like cement paste, we are having studies on the CSH.
I think you are saying that some CSH is
Added as a mother liquor.
Synthetic CSH is added to your system.
As a mother liquor.
Right? So will it affect the formation of the CSH?
You are saying seeding with CSH?
Yes.
That's right.
Yes.
That's right.
Okay.
That's right.
I have not explored that,
Okay.
but
Okay.
yeah.
Not an issue. You can discuss that
Thank
later
you.
on.
Thank you.
If it is a quick one, you can go ahead.
I was expecting a question from you. Yeah.
Yeah, sorry. So I have worked on CSH a lot, so that's why sorry for that question. So when you say that with calcium silicon ratio, the strength is decreasing, or
Not the strength, elastic modulus only.
okay,
Modulus only, yes.
modulus only.
Yes, sir.
So just look at some paper from Goicheng Geng, because many of these might be just simulations. Simulations cannot be relied. I do simulations, so I will say it that way. And also see the difference between synthetic CSH and CSH that you get from cement hydration. Can be different properties. Thank you.
Okay, sir.
Okay,
Thank you.
so thank you very much, Mr. Amit, and all the best for your future work. We move on to the next presentation, a comparatively thermal study of sustainable limestone calcium clay cement and ordinary Portland cement concrete beams at elevated temperature. Bhandari, yes, S, right? Okay. You have 8 minutes to go, and 2 minutes keep separate for the interaction.
Thank you, sir. So I am MSR scholar under Professor Bisnoy, and my topic is a comparative thermal study of sustainable limestone calcined clay cement, LC3 cement, as we know, and between ordinary Portland cement at the elevated temperature for the concrete beams. So these are my outline. So introduction and motivation background, research gap, objective, material and mixed design, results. So basically reinforced concrete is widely used in infrastructure due to strength and durability. But also, why do you use the reinforced concrete? Not only because of the strength durability, but also because of economic point of view. Yeah, but also both are the very vulnerable to the fire exposure. Higher temperatures during fire can cause thermal degradation of the concrete. Also, due to after that, the corrosion may happen, and the steel reinforcement leading to the structural failure. OPC remains the standard binder in concrete. However, the higher clinker content causes significant carbon dioxide emissions, raising environmental concerns. So my motivation of background towards this, why I choose this topic, was this is my part of my research ongoing. It's only the part. So limestone LC3 is emerging a sustainable alternative, reducing up to 30 to 50% in clinker, offering promising mechanical and durability characteristics. Many research has been done on that, and I have quoted some sources too. So LC3 shows promising for better mechanical and fire resistance properties, but again, require detailed comparative studies. And as today morning only Professor Kudur said that there is the reliability of the fire codes has been very less regarding the fire. So also this, my research is going to probably little bit add on to the importance of how this sustainable alternative like LC3 could be helping to study in the fire, regarding the fire. Despite environmental benefits, detailed experimental data on LC3 thermal performance under fire conditions very limited, necessitating to comparative studies with OPC to inform greener and infrastructure designs. So what is the research gap? So current fire resistance design codes primarily rely on the OPC data, as I mentioned earlier. So creating need to explore emerging sustainable blindness like LC3 to revise guidelines and improve the performance predictions. So again, a need for fire performance data on LC3 also is required with various replacement and strength levels to inform modeling and codes. So my objective is to quantify the time temperature profiles from 400 to 1000 degrees in which reinforced concrete beams are made. So assess how LC3 replacements percentage from 30% to 50%, and how does the grade affects and comparing with the OPC. So and provide a recommendation for the LC3 mixed design and update fire safety standards. So what are the material and mixed design that I have done? So I have taken the OPC M25 and M50. Also replacement of LC3 has done with 30% and 50% clinkers for both grades. And water to binder ratio I have taken for 0.3 and 0.45. And the what concrete beams that I have casted is 750 millimeter length into 150 into 150 with the various that OPC and LC3 varieties. Also that I have kept, I have placed 3 thermocouples inside the beams and kept for the elevated fire. So these are the results. So for these are the temperature profile that I have observed for the 400 degrees centigrades. The OPC gives very steep curve. So the curve that I can show you the green side. Oh, okay, I'll use the pointers. This is the M50. The M50 curve. The M50 curve is the green one. It shows very less with the thermal diffusivity of the LC3 is very less. It shows very less, and the steep rise of the that we have shown the figure in the both OPC and OPC M25 and OPC M50 that I have taken the examples for the steel curve. Why steel I have chosen out of those 3 one is the OPC M25, the behavior still is like faster rise in the high peak. It gives a very high peak of the in the temperature curve, and because of that, high thermal conductivity and more portlandite and early micro cracking. Similarly, with the OPC M50 also, that we have seen the same pattern, like higher grade concrete and denser matrix, still good heat conduction. But out of those all, like M50 LC350 is the best performer. It gives the very least peak, and also because of the thermal stability is very good, that it shows from the the curve that I have achieved. Regarding the 1000, because I skipped. Why I skipped? Because of the all between 400, 600, 800 also. But I have presented in my research in in conference only the 400 and 1001. So regarding the steel, again in the same pattern that I have observed regarding the OPC M25 and OPC M50 and LC350. And the same, I have taken the steel example over here, and the OPC M25, the highest peak is achieved in the 900 degrees centigrade, very rapid rise. And it probably is due to the high portlandite content and rapid cracking is seen, but we couldn't see any kind of blasting in the beams. However, the peak of rise of the peak is very high in the OPC M25. Also similarly, OPC M50 also give the same kind of height in the peak. But however, the M50 and LC350 is the lowest of all. And it gives, because of the maximum LC3 gives maximum steel protection, that I can conclude from my research. So results at the 1000 degree temperature profile is like, So again I have taken the flexural strength of the beam at the 27 degrees centigrade normal temperature, 400 and 600 and 800 and 1000 degrees Celsius. Out of here also, like only like LC350, M50, water binder 0.3 ratio gives very much high flexural strength out of all in every department, like 400, 600, 800, and 1000. These are the results that I have concluded from that figure only. As temperature increases up to 4 to 600, the flexural strength also decreases across all blends. Through LC350, water to binder ratio 0.3 consistently retains the highest values, highlighting resilience. OPC mixes, especially at higher water to binder ratios, exhibit the steepest strength reduction with flexural capacity falling below 1.5 megapascal to at 600 degrees. At extreme heat, like 800 and 1000, strength drop further. Yet LC3 blends, particularly LC350, water to binder ratio 0.3, continue to outperform all the OPC mixes. So why LC3 is better? So it's because of lower portlandite content, and as cast gel and plus carbon is there in in LC3, and denser pore structure reduces the heat conductivity and controls the internal vapor pressure. Lower thermal diffusivity, it travels slower. That we show the reducing peak, and improve the residual strength. That also we have seen through the images. So my conclusion is that LC3 concretes with 50% replacement, M25 or MP show the best fire resistance, significantly lowering internal and reinforcement temperatures and reducing the spalling risk. High strength OPC, the OPC 50 perform poorly under fire. Probably poorly may not be the right adjective here to put, but sorry for the word. Providing that mechanical strength alone doesn't guarantee thermal safety. LC3 slowed the heat penetration and controlled cooling, improving overall thermal stability during and after the fire exposure. The result strongly support updating fire design codes to include LC3-based sustainable concretes, especially when combined with reinforcement and protective measures. So I'd like to acknowledge Grantham Project for providing financial support and Cementier for making future same technology available to us. Thank you.
Thank you very much, Mr. S. Bhandari. Quick questions? Anyone? Yes, please, go ahead.
It's a costly experiment. Whether you have, just have a doubt that whether you have that heated the beam to the temperature without any loading, or you have...
No, without loading, sir.
So, in practically, we cannot load and both we cannot do simultaneously, but at least you could have made it some serviceability stress, no? Some inducing the cracks, I mean, with a lower service load condition, then if you test, the behavior will be different. That is the actual scenario.
Oh, yes, you're true. That's right, sir.
Just a quick question. Why you choose for flexural strength, not the compressive strength, when you are testing the high temperature results?
No, regarding flexural strength gives the real scenario rather than the compressive strength, sir, in terms of the fire.
Okay, we can discuss that later on, because what I am trying to say, the variation in the flexural strength is very small. So the scatter of the result when you are testing 1 to 5 MPa,
yes,
and when you are testing 25 to 50 MPa, you could have actually more clearly distinguished, isn't it? Anyway,
yes,
we'll discuss that later on.
Thank you, sir.
So thank you very much. A big round of applause. Very good work. And whatever hurriedly he did, it's because of me, because I put pressure of finishing it. There is GC meeting also to start, so we have to be on time. Thank you very much for managing the time. The next presentation is low carbon and low cost agro-based binder for non-structural elements by Mr. S. Das. So can you just speak up your full name?
My name is Dr. Saikat Das.
Dr. Saikat Das. Dr. Saikat Das, right. So the floor is yours. Please try sticking to 8-minute presentation so that we get 1-2 minutes for any quick question, right? Thank you.
Good evening, everyone. I am Dr. Saikat Das, postdoctoral researcher at Department of Civil Engineering, working with Professor Piyush Chansali. Today I am going to present my research work, low carbon and low cost agro-based binder for non-structural elements. So we know that cement is one of the, cement is a very sodium carbonate. Sodium carbonate only produce 0.3 to let's say 0.5 gram of carbon dioxide if you produce 1 gram of sodium carbonate. So it will further reduce the carbon production. Further, up to granite powder replacement by 20%, it can reduce the quantity of the activators. So it will further reduce the carbon consumption, carbon production. And further, this process simultaneously eliminate the disposal problem of this biomass. And finally, it has potential to eliminate the consumption of the cement. Further, I have observed that most of the cases I got it M14 strength. So I think in non-structural element we can use, if it's more than 5 MPa, we can use for non-structural brick, block, and application. And one of the best advantages is that it can effectively eliminate the two-part activation process. I can give you live example. During my PhD, I was used to with sodium hydroxide. So it is still injured. But due to this process, pH is developed internally. So we are eliminating the sodium hydroxide. So it will provide the safety to the our worker. Further, at the production plant, we just simply mix the activator, and at the site, we can simply mix with water and course fine aggregate, and we can prepare the mortar or some kind of matrix. And I thankful to our center, Technologies for Low Carbon and Lean Construction at Department of Civil Engineering, IIT Madras, and special thanks to ACECON and our Instrumentation Facility Center for all the instrument, and special thanks to SRB because without funding this research is not possible, and Ministry of Education of our country. And for further low carbon and lean construction, you are all welcome to our BTCM family. And these are my references. Thank you.
Thank you very much. Thank you very much, Dr. Das. And nice presentation and good direction. I'm impressed by the direction taken and the work you are doing. Any questions from the audience? Sir.
Yeah, indeed a good presentation. So, have you think about extending your results to structural geopolymer, where if you can eliminate sodium hydroxide and sodium silicate, is it possible?
It is a kind of a hybrid process. It's not a geopolymer. It is an alkali activation. It's an intermix of both polymerization reaction little bit and hydroxide. So it is a kind of one-part activation. I'm not using any hydroxide or this system. So I'm using just carbonate system to cross-linking the silicate network, because in glass system, all the silicate network is made by SiONA. So when you add water, it will increase some changes the pH and it will dissolve. And over time you'll find a reduction in strength in underwater cases. But in my cases it is a cross-link structure, so it will attach each other unit and it will provide underwater stability.
Right. Any other? Right. So thank you very much. Thanks for a nice presentation. And we move on with the session. Dr. Deependra Das. Yes. So I awarded your PhD. Your supervisor, I hope he is not present here. He's here. So you are not required now. My apologies. So the molecular level investigation, alkanolamines in cement hydration. Please. And please take 8 minutes and 2 minutes for the quick questions.
Good evening, everyone. I'm Deependra Kumar Das, PhD scholar in the Department of Civil Engineering at IIT Madras. I'm working with Professor Aslam Kuni Muhammad. The title of my today's presentation is Molecular Level Investigations of Alkanolamines in Cement Hydration. So the outline of my presentation consists of background and introduction on chemical admixtures, followed by motivation, and then I'll be introducing about alkanolamines, and then some of the results based on simulations as well as based on experiments, followed by concluding remarks. So in modern concrete, chemical admixture is the must needed. So for instance, if you talk about the application of precast or tunneling work or for shotcreting, there is a need of accelerators. Similarly, if you're talking about a 3D printing or SCC, there we need high-range water reducers or even
some modified chemical admixtures such as VMAs, that is viscosity modifying agent. So for tailoring the properties of concrete, we need the various chemical admixtures. So often in field, we'll always see there will be some incompatibility between chemical admixtures and cement, which could leads to the loss of the slump, or else even it will retard the setting time, and even often we'll see some strength gain loss. Basically, these chemical admixtures act as a molecular label. So here in the figure, oh sorry, here I can do, yeah. So here in this figure, you can see that how the chemical admixtures, here it's a PCE-based chemical admixture, how it is acting on the cement grains. So here you can see that the on C3S surface, it is filled up with water as well as the chemical admixtures. And then we can perform some simulations just to understand the mechanism of interaction of this chemical admixture. So based on this, my topic will be basically related to the accelerator. So in accelerator, we can see that so we need some alkanol amines, which will be in the dosage of 0.02 to 0.25% by weight of cement. And then that accelerators will be adding to the concrete in the percentage 1 to 5% by weight of cement. So for my research work, I'll be talking about 3 different alkanol amines, so which is TEA, triethanolamine, triisopropanolamine, as well as diethyl isopropanolamine. So basically, these 3 molecules differ in structure just by 1 or 2 methyl group. If you see TEA, there will be a nitrogen atom in the center followed by 3 side chains with hydroxyl ion. But in triisopropanolamine, we have one hydrogen will be replaced by 1 methyl group in all the side chains. But in DIPA, it's only one H will be replaced by methyl group. So there are many applications of these alkanol amines. So many researchers have worked as a grinding aids. Even now people are exploring about this chloride binding capacity, and then even carbon CO2 sequestration or mineralization, where it can react with the calcium with CO2 to form calcium carbonate. So basically, if you see, it's a rate of heat flow curve with and without adding of this accelerator, where the dosage of this accelerator is 0.02% TEA. So you can see that initial dissolution curve, it's represented by 1, and then induction period, followed by here we can see that with the accelerator, we can enhance the C3S hydration, followed by we have a C3A, secondary C3A depletion peak. So based on different research, so many researchers, they have concluded that TEA can act as accelerator in the dosage, the lower dosage, that is 0.02 to 0.05%. But if you increase the dosage beyond 0.1%, it shows the retardation effect. And again, it shows the acceleration effect if you are increasing the dosage beyond 1%. But there are many contradictory results. Some of the work from China, they have suggested even at the lower doses, that is 0.02 to 0.05%, it doesn't show any effect. But even I conducted some of the research, yeah, it's showing pronounced effect with these alkanolamines. So based on this, there is a need to study the interactions of these alkanolamines with the cementitious system. So basically, for the research purpose, this is the percentage that for these 3 different chemicals used in the research. For TEA, it's a 0.1%, while TIPA, it's a 0.05%, followed by for DIPA, it's a 0.03%. So these are for the research purpose. Now talking about there are the different kind of hypotheses they have, it's provided, different authors have reported. So basically, it can even form a complex with the calcium ions that is present in the cement, or it can form a complexes with the yttringite. So there are many different hypotheses. So this is a rate of heat flow curve with lower doses of alkanolamines. We can see that the rate of C3S hydration and the secondary, this C3A reaction is prominent with the addition of these alkanolamines, and even you can see that the AFT to AFM conversion is prominent. But at higher doses, if you see, so at higher doses means beyond 1% or even 0.1%, we can see that the C3A peak is moving towards the left, while the C3S hydration is retarding. So you can see that with the increase in the doses, C3S reactions are getting delayed. So there are much work that is needed to understand this kind of chemicals. So even there are some studies that reported that the morphology of the hydration products can even change. That is the Portlandite. So the hexagonal shape of Portlandite can change into actinomorphic small crystals. And even the AFT phase is getting changed, that is ytringite. So and the people have reported that this AFT and then Portlandite that can enter in the CSH and can even affect the C/S ratio, that is calcium to silica ratio. But there is no supportive literature or the simulation works that people have conducted till now. So if such things are there, if CSH is getting affected, means yeah, there can be effect on the strength as well. So for my study, I have started with the simulation of this TEA molecule with the interaction of this calcium with the help of this quantum mechanics, that is AIMD, ab initio molecular dynamics simulations. And then here I have done this complexation energy calculation. So before starting with this, what is this classical MD and then AIMD? So AIMD is ab initio molecular dynamics, which calculates the force based on the electronic structure. And that uses the principle of DFT, density functional theory. But here we have the limitation of the number of atoms. So the number of atoms can be more maximum up to 800. And then even the capturing the snapshot, it will be in picosecond, which is, I don't know whether the civil engineer will believe these things or not. But then for just to understand much more in realistic condition, we will be performing some classical MD. So that is based on the force field parameters. If our force field parameter is better, we can get a more accurate result. So here we can even play with the more than 1,000 or 10,000 atoms. That can be a realistic condition. So based on these things, I have started my simulations where I have a box of 20 angstrom box. In that I have a TA molecule with a water of density 1. So I have considered the collective variables, which is the variables that is of my interest. For in my case, it's a complexation as well as the distance and the coordination number. So this is the time versus distance, time versus this collective variables plot, how it is changing over the time. And then I have done this AIMD, it's a well-tempered metadynamics. Here I am putting the bias, that is the Gaussian hills at each time step, and then just to see the this FES, that is free surface energy, how the system is exploring at different transition states. Here I saw like with the bias of 20, that is the 20 bias, it shows that like the distance between calcium and the center of mass of TA molecule is nearby and the coordination is there. So but at a higher bias factor, it shows the artifacts issue, which is the periodic boundary condition. So at half of the simulation box, it will show some lowest free energy. So what I found was the lower bias is needed for the small size box. So parallelly, I have done some experimental work where I have seen like with the lower doses, it shows the acceleration effect, but at 0.1%, it shows some reduced induction peak. But with different water to cement ratio, I tried to keep the concentration of the ion same, but here I could not get the same result. If you see about the 0.08% TA with 1.58 and then 0.02%, here the concentration is same because in one system it's the water to cement ratio is 0.4 and here 1.58. I tried to keep the concentration same, but I could not able to achieve the similar rate of hydration peak. So that means there is some adsorption mechanism that is playing some role. So similarly for TIPA, I did some of the experiment where I can see the C3A peak is more C3A peak is more prominent in terms of TIPA. And then rate of heat flow is even bit more compared to TEA, where you can see it's a 250 around, but in that case 200 something was there for the TEA. And even I saw like that the higher doses of 10% or 8%, it shows like the delaying C3A hydration, but the C3A peak is prominent, which shows that the C3A or even C4AF hydration is happening. So still some more things, some more experiment I have to conduct. And then based on this, I have concluded that TEA is showing lesser rate of heat flow compared to TIPA, as well as at the similar water to cement ratio, I could not able to get the same heat flow curve, which could be because of the adsorption mechanism. And then at higher percentage, C3S hydration is prolonged. So for the future, I'll be conducting like the similar simulation setup with the other ions, that is like aluminum, iron, and again calcium with the TIPA, DIPA, and with some of the surfaces of Portlandite and CSH. and then I'll try to find the complexation and the adsorption energy on those surfaces, and I'll conclude like which surfaces or which complexation is the more stable compared to others based on the free surface energy. So these are the references. Yeah, thank you.
Thank you, Mr. Das. And sorry, due to paucity of time, I think I have lots of questions actually, but we will discuss that later on.
Yeah.
Thank you so much.
Yeah,
the next speaker is Mr. Kamla Purkar, magnesium silicate cement, a carbon sequestering material for advancing environmental sustainability. So I request you to take 8 minutes, right? I'll give you just a hint, and then.
Yeah, very good evening to everybody. Myself, Dr. Brij Bhushan, working as a regional coordinator for R&D cell in the Department of Civil Engineering, and I am presenting this paper along with my student Samrudh Kamlapurkar. Magnesium silicate cement, a carbon sequestering material, as explained in the morning by our SP Shah sir. We have to save cement not because it is expensive or it's costly, it's because it's an carbon emission material, it has a carbon liberating material. Here in this study, we are using magnesium silicate component, in fact, in the substance of a raw material, which is a generation of MSH gel. Instead of CSH gel, here we can see magnesium silicate gel presentation. Okay, this magnesium silicate gel is as same as CSH gel, which liberates it, and also you can see aggregate needles which are generated in the same form, but this generation is more concentrated, it attracts more energy, and it forms more strong bond compared to your ordinary Portland cement. And here we are also trying to study different this thing in the SEM and SEM analysis and XRD analysis, where we can see the generation of generation of these aggregate needles. I will tell you in our own scenario, unlike these things are not LNT and not our contractors are not LNT. We are working, SP Anchuri sir know that where we have come from. Our contractors are Government of Karnataka. We have to thank Government of Karnataka as well as Government of India. They are supporting us to study these statistics. Our contractors, where we are working, where we are coming from, they are least bothered about these statistics. Okay, that is 11% generation of carbon material and 7% generation of carbon material from the cement. They are least bothered. We should be thankful for the Government of Karnataka. They are, they are supporting us to study these statistics and use magnesium silicate material. The magnesium silicate material is a raw material, but we are supporting in our paper to use an industry waste. We are supporting an industry waste. Also, we are supporting to add some of the steel fibers, some of the polypropylene fibers to increase this magnesium silicate gel to form good strength. Basically, here we are studying the microstructure, and my student Samrudh Kamlapurkar will take the stage to explain those XRD cells and ACM cells here. Thank you.
Thank you, sir. Like has sir has said that we need to understand that why the carbon dioxide, the carbon sequestering material is necessary. As for now, you can see that from the data given here, that the maximum of the carbon dioxide is released from the cement industry and cement production from the cement production, which is higher in the countries like India and China majorly. And you can see here in the data that the majority of the carbon dioxide emissions were from China, India, and next is US. And coming to the rest other countries, it is half of the production, cement production, as we compared to the us. So it is like we can see that carbon footprint of OPC is like 0.9 tons carbon dioxide per ton for the production of OPC, because and during the production of cement also, the energy we create for the production of cement from the clean From there also we releases the carbon dioxide. So to think of the alternative, we are going for the magnesium silicate cement, which is an alternative binder for the OPC. Here the magnesium silicate cement, we can see that here MgO reacts with the water to form magnesium hydroxide, and this magnesium hydroxide will react with a silicate component to form a magnesium silicate hydrate. The magnesium silicate hydrate is in a it is in a gel which acts as a CSH. And later on, this magnesium silicate hydrate reacts combines with the carbon dioxide to form magnesium carbonate and also silicon oxide, SiO2. This magnesium carbonate in this magnesium silicate cement holds the carbon dioxide, and it will not releases the carbon dioxide later on, as like of a OPC. This magnesium component, magnesium oxide, is majorly found in two minerals. Like one is olivine, which is rich in magnesium MgSiO4, and it is also rich in FeSiO4, which is forsterite and FeAl. This structural composition is orthorhombic crystal system and found in an igneous rock like basalt. Here we can see the reaction that when Mg2SiO4 reacts with the carbon dioxide and water, it forms MgCO3. And the second mineral is serpentine, which is a composition of again the Mg3Si2O4 with the hydroxide thing, which is contains hydrated silica, makes it reactive for cement applications. So when we see in the table that the aspect ratio of carbon emission for magnesium silicate cement and ordinary Portland cement OPC, carbon emission is almost negative and low, whereas OPC is very high. Main reaction is carbonation in MSC, but in OPC it is an hydration. Binder phase is MSH, OPC is PSH, and carbon dioxide role is absorbed, whereas in OPC it is emitted. So when we come to the mechanical strength and durability of these cements, if we see to the compressive strength, we can go up to 40 to 80, varies according to the mixers, but in a Portland cement will be it will be till 30 to 60 unless we perform some UHPCs. So again, coming to the flexural strength, we can gain up to 5 to 10 MPa, whereas OPC 4 to 7 MPa. Sulfate resistance, it is excellent due to the no reactions of sulfates there. But in a Portland cement, it is a moderate and poor, and acid resistance high in a MSC, whereas it is low in a OPC. Chloride penetration is low, but in OPC it is a moderate. Carbonation strengthens the structure, whereas in OPC it weakens the structure. Shrinkage lower the OPC, lower than OPC, and Portland cement is higher. Coming to the thermal and fire resistance, it can be stable. MSC can be stable up to 800 to 1000 degrees Celsius, whereas OPC from 400 to 500. Fire resistance excellent. Thermal conductivity 0.2 to 0.6, but in Portland cement it is only 1 volt per meter Kelvin. And when toxic gas emission, it is none in both the cements, and strength retention retains integrity at the high strength also. This is a microstructure of microstructural characteristics. We can see the first two images there. We can see that porosity is densely it is dense matrix, so that we can see that less porous amounts, and whereas when in OPC, which is the lower down, the thing due to the CSH gel, we have weak and vulnerable things. So environmental advantages due to the less of time, like we can reduce the carbon dioxide emission, and we can absorb the carbon dioxide. So whereas this MSC absorbs 1 ton of carbon dioxide per ton of cement produced. So coming to the comparative data, this is a comparative data of MSC and OPC. But when I come to the resource availability, the last thing, the resource availability in India, we have a lot of raw materials with respect to the MSC thing. We can majorly see in the belts of Odisha, Karnataka, Tamil Nadu, Northeast India, Rajasthan and Maharashtra. But mainly to look after into the availability through the byproducts of industries, so that we should not utilize the natural earth. So if we see the raw materials, the byproduct is steel slag, ferrochrome slag, nickel slag, asbestos, founder of aluminum waste. These are the materials where we can see the MSC availability. So challenges and the future directions, obviously the cost and scalability. The cost is high at the initial stage, but in a scalability, if we scale the thing, then we can reduce the cost. Research and development, there is a lot of research and development need to be done. And you can see in the figure that the supply chain is less for this cement because of the magnesium availability of the thing. The shaded yellow region where the magnesium oxide is easily available. So we need to manage the supply chain of it. So coming to the conclusion, this OPC contributes less 8% of global carbon dioxide emissions. So that to avoid it, we need to take alternative binding material, that is MSC. So this is a step towards greener production. These are the references. Thank you.
Purkar, because we have already exceeded time, so my apologies for not discussing the topic right now. Yes. Just after that we can. So now we are coming towards the close of the session. Now the last speaker, Mr. Soumya Narapalim, synergistic utilization of alcofine and sugarcane bagasse ash for enhancing strength and durability of sustainable concrete. So floor is yours. Yes. You can take just 8 minutes and maybe leave some time for discussion. Thank you.
Good evening, respected chairperson and all the professors and my dear delegates. So myself is Dr. Katkonda Naresh, and before going of this, my presentation today, we are now every and morning to still now we are discussing related to the sustainable aspect and low carbon related of the things. So this is a project is done our UG students. These students came from the Nizamabad district in Telangana region. This area is most of the agriculture farm is, it is related to the sugarcane ash. So the wastage of their own agriculture farm, so they were converted into sustainable aspect for the future low carbon concentration point of view. So the title is the synergetic utilization of the alcofine sugarcane bagasse for the enhancing the strength and durability sustainability concretes. Here, the overview of this presentation is introduction and literature review, the motivation of the research and the problem statement, and the materials, the fresh and mechanical properties of the concrete and durability property of concrete, and conclusions and reference. These are the outline of today my presentations. And the introduction, we know that the concrete is the second most widely used material after the water. But the major problem is the concrete is not the problem. The problem is the cement is the problem, because the production of the cement, while production of the 1 ton of the cement, the equal amount of the carbon dioxide will be releasing the outside of the emission. Simultaneously, we are utilizing the natural resource of the materials, we are losing the natural resource of the material, and it affecting the environment pollution of the things. So for that, the huge energy demand carbon emission associated with the cement production, it is related to the creation of the serious environmental pollution effect. For that, it is related to necessary things we have to take the steps related to the sustainability concept. So for the sustainability aspect, we replace the cement with the using of the different binder materials. So that is the binder material, majorly we can use the fly ash and GGBS and sugarcane ash. There are a lot of different materials we are using for the optimal replacement of the cement for the enhancing the strength properties as well as durability from the environmental aspect to protect the natural resources as well as to control the pollution point of view. But we are using in this project the replacement of the agricultural industrial as well as industrial wastage material, the partial replacement of the ordinary Portland cement. The major approach of this is to waste to wealth conservation as well as circular and economic principles, and the reduction of the landfill dumping and the low environmental footprints. These are the 4 major aspects to utilizing of this project with the replacement of various proportions with the sugarcane ash as well as alcofine. So we already done the lot of the research is previously with using of the fly ash and GGBS and alcofine blended concretes. So however, there are limited investigations is done with using of the alkafine and this sugarcane ash. So there is a scope to determine the mechanical and durability aspects for the sustainable construction point of view. So is the gap we can focus on, especially the what they are having the local available wastage material to conversion of the sustainable aspect. So they are done the BTech level, UG level of the students. So for that they are done what they have done that project for the encouragement most purpose, of the material convert this paper as this conference purpose. We are using so only 50% of major motivation for the India having the largest sugar cone material is so the major scenario for that 90 to 100 million affecting for the landslide among of that it will be converted 10 to the major millions of tons sugar related to pollution. So the most of the so material we are not utilizing the emission and creating we are using only 50% of sugar cane so as utilizing of the utilizing of the and alka so the major scenario for that it is for the affecting for the one is the land reduction of the cement consumption condition and second one the major serious environment related to the agriculture industrial waste. So for that the contribution developing the sustainable creating OPC development of low carbon emissions M30 grade of utilizing of the so the here SCBA and conducting alkafine we are utilizing the OPC ordinary for offering for the dual advantage. One is the reduction of the cement consumptions M30 grade of the concrete utilizing of the large volume of agriculture 0 to 30% and 0 so we are developing the sustainable OPC development 30% the concrete M30 grade of the concrete and the alkafine is we can keep conducting 5%. We are utilizing the we have done this mixed design. You can see that these are the various procedures for the preparation of 30 grade of the concrete. Sugar cane ash to direct mix to the OPC. If this done 30% students only they are coming from collecting of this wastage material up to the 30% own farmhouse. Then we are utilizing and the alkafine is we can keep a constant 5%. And we have done these are we have done this mixed design. Initially we have done the reference mix with using of OPC preparation of and then we have replacement of the alkafine mixed to the OPC. Then we replacement of the sugar cane ash 5 and 10 and 15 and this wastage material 25 up to their own farmhouse. Then we are utilizing for so for this we examined for the fresh and we have done as well as mechanical and durable. Initially we have done the for this reference mix with using of OPC examine only and then we have you can observe that the alkafine using of the OPC replacement of the 90 mm of the slab and 10 while replacement of the alkafine we get the 95 mm while replacement of the alkafine with the sugarcane ash. So for this we examine observe that the slump will be as well as mechanical reductions will be happen. Because the sugar cane has having only very fine material. You can observe that absorb the water content it is reduction of this work 90 mm of the slab. Optimum while replacement of the alkafine we get the 95 mm while replacement of the alkafine with the sugar cane behind of that we can observe that the slump will be and little reduction we can conduct the mechanical properties for the compressive strength. You can see that very fine compressive strength for the 7 absorb the water content it is reduction of this workability for the so 7 days 22 MPa for the ramp is 28 days 10% MPa. We get with the replacement of the 5% of alkafine you can observe that it will be reduction of this slump 38 MPa. But the similar trend is observed that we are impressing compressive replacement of this. You can see that alkafine using of ACECON the compressive strength for the OPC cement. So the optimum 7 days 22 MPa for the with the replacement of the 30% of the with the replacement of the 5% of alkafine. Behind of that it will be reduction of the strength. You can observe that the fresh properties will be but the similar trend is observed that we are impressing well replacement of this but alkafine we can observe using of ACECON the compressive strength also increase the mechanical so the optimum compressive strength because having this with the replacement of the having the very fine material and it is having the more content of the silica behind of that it will be reduction of the strength you can observe that the fresh properties and you can observe that the same trend is observed in the spilt as well strength also But
with using of
simultaneously
the
you can observe that
F-
what replacement
OPC
of
cement
maximum
grade,
percentage
we
of
get the
ACBC,
2.7
the mechanical
MPa
property will be
with
increased.
replacement of
Because
the
having
5%
this
of
ACBC
alkafine,
having
we
the
get
very fine
approximately
material and
3.1
having the
MPa,
more content of
and
the silica,
increasing this
ACBC
compressed to
the
strength of this
maximum
material.
fill tensile strength
And
you
you
can
get
observe that the same
3.4
strength is
MPa.
observed in the
So
fill
the
tensile
optimum
strength also.
tensile
With
strength
using
will
of
get
the 30% replacement of the
OPC cement grade,
ACBC.
we get the
So because it
2.7
having this
MPa
cement as a
with
material,
replacement of the
alkafine is a
5%
very
of
fine material
alkafine,
and
we
will
get
affect the
approximately
flare effect
3.1
and it
MPa,
generates in
and
the
increasing
CSH,
this
secondary generation of
ACBC,
gel, and
the
it is
maximum
the pozzolanic
fill tensile
activity of
strength
the
we get
ACBC.
3.4
So due to
MPa.
these
So
two
the
material,
optimum
it enhance
com-
this
tensile
the
strength will
optimum
get
percentage of
30%
the
replacement of the
ACBC.
of ACBC.
So because it having this
You can
cement
observe
as
that
a material,
the
it
same trend is
alkafine
observed in the
a very
flexure
fine
strength also.
material and will
Here
affect the flare
the
effect
0%
and
of
it
the
generates in the
ACBC,
CSH,
we are
secondary
getting the
generation of
approximately
gel and
3.6
it is the
flexure
pozzolanic
strength,
activity
while
of the
increasing this
ACBC.
ACBC,
So due to this
the maximum
material, it
fle-
enhances
flexure
the tensile
the
strength, we
optimum
get
percentage of the
4.6
M30.
MPa. Due to that,
Mixed
the
proportion
improved
of
the matrix
ACBC.
disintegration and
You can
strong
observe
based
that
on
the
aggregate
same trend is
interfacing bonding,
observed in the
the
flexure
formation
strength
of
also.
additional
Here
CS gel and
the
going
0%
into command
filler
filler
actions,
actions,
the alkafine and
we are getting the
pozzolanic
activity of
approximately
ACBC.
3.6 flexure
Due to
strength,
that, the
while
flexure strength
increasing
also
this
increasing. We
ACBC,
conducted after
the
that
maximum
durability test in
flexure
water
tensile
absorption,
strength
we get
in the water
4.6
absorption for the
MPa.
OPC cement,
Due
we
to
get
that, the improved the matrix
4.2%
disintegration
while
and strong
increasing this
based on
5%
aggregate
of
interfacing
interfacing
bonding,
bonding,
the formation
we get
of additional
this,
CS
the
gel and
approximately
going into command filler
2.3%
actions,
was
the
done
alkafine
the
and
minimum
pozzolanic
water absorption.
activity of
So compared to
ACBC.
the ordinary
Due to
Portland
that, the
cement,
flexure strength
with
also
using of
increasing. We conducted after that
ACBC
the
30%, we
durability
get
test in the water
45%
absorption.
of
In the
reduction
water
of the water
absorption for the
absorption.
OPC cement, we get
45%
45%
of the
while
water
increasing the
absorption
5%
with using
of
of the
replacement of
OPC
alkafine.
cement.
We
And
get
similarly,
this, conduct this
the
activity
approximately
and the same results we
2.3%
obtained
was
the
done the
results we
minimum water
obtained with
absorption.
using of
So
ACBC
compared to the ordinary
and
Portland
after
cement,
conducting, we
with
conducting
using
the
of
ACD resistance also,
ACBC 30%
in approximately
we
the
get
OPC cement, we get
45% of
2.8%
reduction of the
while
water
increasing
absorption.
of this,
We get
ACBC
45%
the
of
maximum
reduction of the
percentage
water
1.1%
with using of the
nearby
OPC cement.
60%
And
improvement
similarly,
in
conduct
acid
this
resistance
activity
compared to with
and
the same
normal
results we
concrete like a
obtained,
OPC
the
concrete.
similar result we
So because
obtained
with
with
using of these things, the reduction of
and
calcium
after
hydroxide
content
and also
the
define the
ACD
post
resistance
and
also
dense
in approximately
CSH
the
gel
OPC
formation,
cement, we get
it reduction of the
percentage while increasing of
ACD,
this
ACBC, the maximum percentage,
so the impact innovation is development of
nearby
sustainability
60%
and
improvement
penetrate
acid
OPC
resistance
binding
compared
system
with
alkafine and OPC,
normal concrete like a
ACBC.
OPC concrete.
And the final
So
conclusion
because
is
with
the
using
professor
of these things, the
investigation
reduction of
30 grade
calcium
OPC
hydroxide
concrete
content and also
define the
5% of
dense
alkafine
CSH gel
formation,
of
it
ACBC.
reduction of
The
the
mechanical
the
properties improved of
ACD
20 to 25% of replacement of ACBC.
So the
and
impact
the durability
innovation is
property
developed
of
also
sustainability
reduction will
and
be
penetrate
up to
OPC binding
increase in
system
20
and
to 25% of the things.
ACBC.
So the durability
And the
result
final
confirm the
conclusion is the
sustainability reduction of water
investigation
absorption
M30 grade of OPC concrete incorporation of 5% of alkafine and 0 to 30% of ACBC. Mechanical,
The mechanical properties improved of 20 to 25% of replacement of ACBC. And the durability property also, a reduction will be up to
Thank you very much,
25% of the things. So the durability
we are
result
now
confirm the
to the
sustainability
close of the
reduction of
session,
water absorption
and
significantly
it was
acidic
wonderful
and
starting
effect of
with
reduction of the
a very apt topic of
and the future scope
overview
we
of
conduct
the
for
Mumbai
the
Coastal
mechanical,
Road,
microstructural
where
characterizations
Dr. Vishal
and evaluation of life durability
outlined how
characterizations. Thank you for
it is going
giving
to
this
impact
opportunity.
carbon emission greatly. And
thank you
then
very
the
much,
session
Dr. Soumya.
Actually went on some of
So
the
we
very
are now
interesting
to the
and
close of the
thought-provoking,
session.
and it was wonderful
topics,
starting with
from
a very apt topic of
mechanical
the
modeling,
overview of the
Mumbai Coastal
thermal
Road
study,
where
and
Dr.
few
Vishal
of the more things
outlined
where
how
more fundamental work
it
is
is going to
required to
impact carbon
go to emission
different
greatly.
directions
And
of,
then the session
the
actually
low carbon
went on
emission.
some of the very
So thank you
interesting
all
and
for
thought-provoking,
being a very good
topics
audience
and
from
giving a patient hearing. Thank
physio-mechanical
you all.
modeling. Thank you very much. Thermal study and
I should say
more
our
fundamental
session
work
chair,
is required
Professor
go
Anurag Mishra
different
sir has done a
directions
really
of,
good job in
the low
finishing
carbon
off the,
emission.
wrapping
So
up the
thank you
session
all for,
by pressurizing the candidates.
being
But
a very
it
good
was a really a
audience
good
and,
session.
giving a
All the
patient
topics, all
hearing.
the papers were
Thank
really
you all.
beautiful. The work
Thank
which
you
has
very
been
much.
done has been commendable to be seen. And we had a
I
beautiful
should
session,
say,
seeing your
our session
practical
chair,
work, sir. We do
Professor
get motivated by
Anurag
seeing
Mishra
all this,
sir
and
has done
I
a really
request,
good
or,
job
I
in,
should say, all the
finishing
current
off
young
the-
engineers
wrapping up
should
the
be focusing
session,
on
by
whatever you have
pressurizing the
done,
candidates,
and they
but,
should be learning
it was
from
a
that.
really a good
Thank you, sir,
session.
for your session.
All the topics, all the
So
papers
now,
were really beautiful.
I
The work
request
which has been
Dr.
done
Abhay
has
Babole
been
sir from
commendable,
VJTI
to be
Mumbai.
said.
And
To
we had a beautiful
felicitate our,
session,
session
seeing
chair
your,
as well as the keynote
practical
speaker.
work, sir.
I
We do get
request Anurag
motivated by
Mishra
seeing
sir
all this, and
to come
I
onto the
request,
dais.
or I should say, all the current young
So
engineers
please give
should
the
be
momentum
focusing
to
on
Anurag Mishra
whatever
sir.
you have done, and they should be learning from that. Thank you, sir, for your session. So now, I request Dr. Abhay Babole sir from
I
VJTI
now request,
Mumbai
Vinay
to
sir,
felicitate our
Vishal sir,
session
Vishal
chair
sir,
as well
sorry.
as the
Vishal
keynote
sir.
speaker. I request Anurag Mishra sir to come onto the dais. So please give the momentum to Anurag Mishra sir. Thank you, sir. Thank you so much, sir. I now request Vinay
that's all
sir
for today's session. We'll
Vishal
meet
sir,
tomorrow
Vishal sir,
exactly
sorry.
at 9:30.
Vishal sir.
Thank you.
Thank you, sir. Thank you so much, sir. Thank you. That's all for today's session. We'll meet tomorrow exactly at 9:30. Thank you.